The more we explore the universe, the more questions we uncover, many of which have no clear answers. But one question has haunted scientists. How did the universe create itself? Did it emerge from nothing, as some theories suggest? Was there a force beyond our understanding that set everything into motion? Or has the universe always existed in an endless cycle of birth and destruction? From the mind-bending concept of the Big Bang to the possibility of a multiverse, join us as we unravel the greatest mystery of all, how reality itself came to be. The Big Bang Theory is the leading explanation of how the universe came into existence and how it has been expanding ever since. It suggests that the universe began as an extremely hot, dense point and has been growing larger over time. Scientists use different versions of the Big Bang model to explain many important cosmic mysteries, such as why certain light elements like hydrogen and helium are so common, why there is a faint glow of energy spread across the universe called the cosmic microwave background radiation, and how galaxies and other massive structures formed. One major idea linked to the Big Bang is something called cosmic inflation. This means that in the very first moments after the universe began, it expanded at an unbelievably fast rate. This rapid expansion helps explain why the universe appears so smooth and uniform in all directions. A vast amount of scientific evidence strongly supports the Big Bang Theory. And today, it is almost universally accepted by scientists. Detailed calculations based on the universe's expansion suggest that the Big Bang occurred approximately 13,787,000,000 years ago, which is considered the age of the universe. By rewinding this expansion using the known laws of physics, scientists have determined that the early universe was unimaginably hot and dense. However, they still lack a complete theory that can describe exactly what happened in the very first moments of the Big Bang. As the universe grew larger, it also cooled down, allowing tiny particles to come together and form atoms. These early atoms, mostly hydrogen, along with some helium and lithium, eventually clumped together under the pull of gravity with the help of an invisible force called dark matter. Over time, these clumps of gas turned into the first stars and galaxies. Observations of distant exploding stars, known as supernovae, show that the universe is not just expanding, it is expanding faster and faster. This surprising discovery is linked to a mysterious force called dark energy, which scientists still do not fully understand. The idea of an expanding universe was first proposed by Russian physicist Alexander Friedmann in the year 1922. He developed mathematical equations, now known as the Friedmann equations, to describe this expansion. A few years later, in the year 1929, American astronomer Edwin Hubble provided observational proof that the universe was indeed expanding. He discovered that galaxies are moving away from Earth, and the farther away they are, the faster they seem to be moving. This discovery is now called Hubble's law. Independently of Friedmann and Hubble, Belgian physicist Georges Lemaitre introduced the idea that the universe began from a single, incredibly small and dense point, which he called a primeval atom. This idea, proposed in the year 1931, laid the foundation for what is now known as the Big Bang theory. The biggest piece of evidence supporting the Big Bang came in the year 1964, when scientists discovered the cosmic microwave background radiation. This faint glow of energy, left over from the early universe, matched predictions made by Big Bang models. Its discovery convinced most scientists that an alternative theory, called the steady-state model, which suggested the universe had no beginning and had always existed, was incorrect. Even though the Big Bang theory explains many things about the universe, there are still some major questions that remain unanswered. Scientists are still trying to understand why there is more matter than antimatter, a mystery known as baryon asymmetry. They are also working to uncover the true nature of dark matter, the invisible substance that seems to surround galaxies and hold them together. And perhaps most puzzling of all, they are trying to figure out what dark energy really is and why it is causing the universe to expand faster over time. The Big Bang theory relies on three key ideas. The laws of physics are the same everywhere. The universe looks the same in all directions on a large scale, and the universe's matter can be thought of as a smooth, flowing substance. The idea that the laws of physics are universal comes from Einstein's theory of relativity. The second idea, called the cosmological principle, means that if you were to look at the universe from any place, it would appear the same in every direction when viewed on a large scale. Finally, a perfect fluid is a way of describing matter in space, assuming it flows without resistance, and that its pressure depends on how much matter is packed into a given space. At first, these ideas were simply assumptions, but scientists later tested them. For example, one way they checked the first assumption was by studying something called the fine structure constant, which controls how light and matter interact. Their findings showed that this constant has barely changed by about 1 part in 100,000 over the lifetime of the universe. The second assumption, the cosmological principle, was tested by looking at the temperature of the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. This radiation is nearly the same in all directions, with variations of only about 1 part in 100,000. As of the year 1995, studies showed that on the largest scales, the universe is mostly uniform, with any unevenness being at most about 10%. The cosmological principle is extremely useful because it simplifies the equations in Einstein's theory of general relativity. This leads to a mathematical model called the Friedmann-Lemaitre-Robertson-Walker metric, which describes the shape and expansion of the universe. By assuming that matter behaves like a perfect fluid, scientists derive equations known as the Friedmann equations, which help predict how the universe evolves over time. At the heart of these equations is a single important number, the mass-energy density. This number determines both the shape of the universe and how fast it expands. One of the biggest breakthroughs in understanding the universe came when scientists figured out what the universe is made of. By studying the way galaxies move and how light behaves in space, they discovered that the matter we can see, stars, planets, and everything that emits light, makes up less than 5% of the universe. The rest is something mysterious. About 27% is dark matter, an invisible substance that affects gravity but doesn't emit light, and 68% is dark energy, a strange force that seems to be pushing the universe to expand faster. Another key concept in Big Bang cosmology is the idea of particle horizons. Since the universe has a limited age and light moves at a fixed speed, there are limits to how far back we can see. Some light from the past simply hasn't had enough time to reach Earth yet, which creates what's called a past horizon, a boundary beyond which we can't observe. Similarly, because the universe is expanding and distant objects are moving away faster and faster, some of the light we send out today may never reach certain distant parts of space. This creates a future horizon, meaning there are some places in the universe that we will never be able to influence. Looking back at the very early universe, we find evidence for a past horizon, But our view is also blocked by the fact that in its infancy, the universe was too dense for light to pass through freely. Over time, as the universe expanded, this horizon has moved farther and farther away. If the expansion of the universe continues to speed up, we may also have a future horizon, meaning some parts of the universe will eventually become forever unreachable. At the very beginning, according to the Big Bang theory, the universe was unimaginably hot and tightly packed together. Then, over time, it started expanding and cooling down, leading to the vast cosmos we see today. However, the moment when everything began, the exact instance of the Big Bang itself, remains a mystery that modern physics cannot fully explain. If we rewind time using Einstein's general theory of relativity, we reach a point where the universe was so dense and hot that all our known laws of physics break down. This state, known as a gravitational singularity, suggests that the universe had infinite temperature and density at some point in the past. But what that truly means is uncertain, as general relativity alone is not enough to describe the extreme conditions of the Big Bang. Scientists believe that during these earliest moments, the effects of quantum gravity, an unknown branch of physics that combines quantum mechanics with gravity, would have been the dominant force. This mysterious phase, called the Planck epoch, happened within a fraction of a second after the universe began, specifically in the first 100 quintillionth of a second, about 10 to the power of negative 43 seconds. At this point, the universe was unimaginably small, with a characteristic length of about 1.6 times 10 to the power of negative 35 meters, and its temperature was around 100 undecillion degrees Celsius, 10 to the power of 32 Kelvin. Conditions were so extreme that even fundamental particles as we know them did not exist. Scientists are still searching for a theory of quantum gravity to fully understand what happened during this period. As the universe continued expanding and cooling, the first major change occurred at 100 billion trillion trillionths of a second, 10 to the power of negative 37 seconds. At this point, something extraordinary happened. The universe underwent a sudden and massive growth spurt, known as cosmic inflation. Within an incredibly short time, it expanded exponentially, far faster than the speed of light. This process smoothed out the fabric of space and drastically lowered the universe's temperature by a factor of 100,000. It also helped explain why the universe today appears so uniform and balanced. Tiny quantum fluctuations that existed during this period were stretched out and magnified, later forming the seeds of galaxies and cosmic structures. Shortly after, at around 1 trillionth of a trillionth of a trillionth of a second, 10 to the power of negative 36 seconds, another significant event took place. One of the four fundamental forces of nature, the strong nuclear force, broke away from the others, leaving only the electromagnetic force and the weak nuclear force still unified. This period, known as the electro-weak epoch, set the stage for further transformations. By the time the universe was 100 billion trillion trillionths of a second old, between 10 to the power of negative 33 and 10 to the power of negative 32 seconds, cosmic inflation had ended. The volume of the observable universe had grown by a staggering factor of 1 followed by 78 zeros. After this, the universe entered a phase called reheating, where energy from inflation was converted into matter and radiation. Temperatures became high enough to create a type of hot, dense state known as a quark-gluon plasma, where the building blocks of atoms, quarks and gluons, could freely move around. At this time, the universe was filled with an intense energy where particles and their antimatter counterparts were constantly being created and destroyed in high-speed collisions. However, an unexplained phenomenon called baryogenesis tipped the balance in favor of matter over antimatter. For every 30 million matter-antimatter pairs, just one extra particle of matter survived. As a result, when all the antimatter annihilated with matter, a tiny fraction of material was left over. This excess of quarks and leptons eventually formed the galaxies, stars, planets, and everything we see in the universe today. Scientists still don't know why this imbalance happened, but without it, our universe as we know it would not exist. These earliest moments of the universe remain one of the greatest mysteries in science. While we have developed powerful models to explain what likely happened, much remains unknown, especially about the physics that governed the very first instant of time. Future discoveries in quantum physics and cosmology may one day unlock the secrets of the Big Bang and reveal exactly how our universe came to be. As time passed, the universe kept expanding, causing it to become less dense and cooler. This cooling meant that the energy of individual particles was also decreasing. During this process, the fundamental forces of nature took on their current forms. One major event in this transformation was the separation of the electromagnetic force from the weak nuclear force, which happened in an incredibly brief moment, about 1/1,000,000th of a second after the Big Bang. Around 100 billionths of a second after the Big Bang, the universe's energy levels dropped to a range that scientists today can study using powerful machines called particle accelerators. By the time the universe was just a millionth of a second old, tiny particles called quarks and gluons started sticking together, forming larger particles known as baryons. These included protons and neutrons, the building blocks of atoms. Because there were slightly more quarks than their antimatter counterparts, called antiquarks, this led to an imbalance, more matter than antimatter. When the universe cooled further, new proton-antiproton and neutron-antineutron pairs could no longer form. This caused most of the remaining antimatter to be wiped out in a massive annihilation event, leaving only about one matter particle for every 100 million that originally existed. A similar event occurred about 1 second after the Big Bang, when electrons and their antimatter twins, positrons, also annihilated each other. At this stage, the universe was mainly filled with leftover protons, neutrons, and electrons, while most of the energy was carried by light particles, called photons, along with a smaller number of neutrinos. A few minutes after the Big Bang, when the temperature had dropped to about 1 billion degrees Kelvin, protons and neutrons began coming together to form the first atomic nuclei, mainly deuterium and helium. This process, called Big Bang nucleosynthesis, laid the foundation for the elements that would later make up stars and planets. However, most of the protons did not combine and remained as simple hydrogen nuclei, which would later become the most abundant element in the universe. As time went on, matter started playing a bigger role in shaping the universe. About 50,000 years after the Big Bang, the gravitational pull of matter became stronger than the influence of radiation. Then, around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with atomic nuclei, forming neutral atoms, mostly hydrogen. This phase, known as recombination, was a turning point because it allowed light to travel freely through space for the first time. The remnants of this ancient light can still be seen today as the cosmic microwave background radiation. After recombination, small differences in density across the universe caused certain regions to attract more matter, leading to the formation of massive clouds of gas. Over millions of years, these gas clouds collapsed under gravity to form stars, galaxies, and the large-scale cosmic structures we see today. The nature of the matter in the universe plays a big role in this formation process. Scientists classify matter into 4 main types: cold, dark matter, warm dark matter, hot dark matter, and baryonic matter, the kind we are made of. According to the most precise measurements, taken by the Wilkinson Microwave Anisotropy Probe, WMAP, the universe seems to follow a model where cold dark matter is dominant. Based on this model, scientists estimate that dark matter makes up about 23% of the universe's total matter and energy, while baryonic matter accounts for just 4.6%. The rest is believed to be dark energy, a mysterious force driving the expansion of the universe. Scientists have found strong evidence from 2 different sources: exploding stars called Type Ia supernovae and the faint glow left over from the early universe known as the cosmic microwave background, CMB, that suggest our universe is mostly made up of a strange and invisible force called dark energy. This mysterious energy is believed to spread evenly across all of space and make up about 73% of the total energy in the universe today. In the very early days of the universe, dark energy was likely present, but everything was packed much closer together. At that time, the force of gravity was much stronger and acted like a brake, slowing down the universe's expansion. However, as billions of years passed and the universe kept expanding, matter became less dense. At some point, the balance shifted. Dark energy started to overpower gravity, causing the expansion of the universe to speed up instead of slow down. Scientists try to explain dark energy using Einstein's theory of general relativity, where it appears as a mathematical term called the cosmological constant. However, they still don't know exactly what dark energy is made of or how it works. Experts are exploring its possible properties through both observations, watching the universe, and theoretical physics, using math and models to understand it. They are also trying to connect it to the standard model of particle physics, which describes the fundamental particles and forces in nature. The way the universe has changed since its earliest moments can be described using a scientific model called the Lambda Cold Dark Matter (LCDM) model. This model combines two important theories: quantum mechanics, which explains tiny particles, and general relativity, which describes space, time, and gravity on a large scale. However, what happened before the universe was 1/quadrillionth of a second old, that is, 1 divided by 1,000 trillion seconds, remains a big mystery. There is no simple experiment or theory that can fully explain that era. Understanding the very first moments of the universe is still one of the greatest unsolved puzzles in physics. The term Big Bang was first used by the British astronomer Fred Hoyle during a BBC radio broadcast in March of the year 1949. While discussing different ideas about how the universe began, Hoyle described one particular theory by saying that all matter in the universe was created in one Big Bang at some point in the distant past. At first, people didn't immediately start using this term, and it only gained popularity in the 1970s. Many people believe that Hoyle used the phrase Big Bang as an insult because he personally supported a different idea called the steady-state model, which suggested that the universe has always existed and would continue forever, without a beginning or end. However, Hoyle later denied that he meant it negatively. He said he simply wanted to create a striking image that would make the differences between the two theories clear. Some historians, such as Helga Krag, argue that there is little convincing evidence that Hoyle was trying to mock the theory. Interestingly, the term Big Bang itself is somewhat misleading. It makes people think of an explosion, but the actual event was not like a typical explosion that happens in one place and spreads outward into empty space. Instead, it was the entire universe itself expanding from a super-hot, super-dense state. Some scientists also pointed out that the word bang suggests a loud noise, but sound waves do not travel through empty space, making the name even less accurate. However, despite efforts to find a better name, none have stuck. Long before the term Big Bang was used, scientists were already making discoveries that hinted at the universe's expansion. In the year 1912, an American astronomer named Vesto Slipher was the first to measure something called the Doppler shift in light coming from distant galaxies, which were then called spiral nebulae. He found that nearly all of these nebulae were moving away from Earth, though at the time people were not sure if they were separate galaxies or part of the Milky Way. Then, 10 years later, in 1922, a Russian mathematician and physicist named Alexander Friedmann used Albert Einstein's equations of general relativity to show that the universe might not be static, it could be expanding or contracting. This idea was shocking because even Einstein himself believed the universe was unchanging. Another breakthrough came in the year 1924, when American astronomer Edwin Hubble proved that the spiral nebulae were actually other galaxies far beyond our own. He used the Hooker telescope, which was 100 inches or 2.5 meters in size, to measure distances to these galaxies. A few years later, in 1929, he made an even bigger discovery. The farther away a galaxy was, the faster it was moving away from us. This relationship between distance and speed became known as Hubble's law and was the first real evidence that the universe was expanding. At almost the same time, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre also came to the conclusion that the universe was expanding. He even predicted the relationship between distance and speed that Hubble would later confirm. But Lemaitre went even further. In 1931, he suggested that if the universe is expanding, then at some point in the past, everything must have been packed into a single, unimaginably small and dense point, a primeval atom, as he called it. This idea laid the foundation for what we now call the Big Bang theory. In the early 1920s and 1930s, most scientists did not like the idea that the universe had a beginning. The dominant view was that the universe was eternal, without a starting point. Some even thought that saying the universe had a beginning sounded too much like religious creation stories. The famous British astrophysicist Arthur Eddington strongly opposed the idea of a beginning, calling it repugnant, because it suggested that matter had not always existed. Many other scientists supported the steady-state theory, which proposed that new matter was continuously being created as the universe expanded, keeping everything looking the same over time. During the 1930s, different alternative explanations were explored. Some scientists proposed that the universe went through cycles of expansion and contraction, while others, like Fritz Zwicky, came up with ideas such as the tired light hypothesis, which suggested that light from distant galaxies lost energy over time, making it seem like they were moving away. After World War II ended, two major competing theories emerged. Fred Hoyle continued to champion the steady-state theory, where the universe was eternal and always looked the same, with new matter forming as space expanded. On the other side, scientists like George Gamow supported Lemaitre's expanding universe model and built on it. Gamow worked with Ralph Alpher and Robert Herman to develop a theory explaining how elements like hydrogen and helium formed in the early universe. These same scientists also predicted that if the universe had once been incredibly hot and dense, there should still be a faint glow left over from that time, what we now call the cosmic microwave background radiation. Though the Big Bang theory was still debated for many years, later discoveries, including the detection of this cosmic background radiation in the 1960s, provided strong evidence that the universe did indeed have a beginning. Over time, what started as a controversial idea became the widely accepted explanation for how the universe began. And it all started with a simple phrase, one that Fred Hoyle never meant to become famous: the Big Bang. It is quite ironic that the term Big Bang, which is now widely used to describe the origin of the universe, was actually coined by someone who did not believe in the idea. In March of the year 1949, British astronomer Fred Hoyle, who supported a competing theory called the steady-state model, used the phrase Big Bang during a BBC radio broadcast. He meant it somewhat dismissively, but the name stuck and became the popular way to refer to the theory proposed by Belgian physicist Georges Lemaitre. For a time, scientists were divided between these two competing ideas. However, as astronomers gathered more observational evidence, especially from radio wave studies, it became clear that the Big Bang theory was the better explanation. The biggest turning point came in the year 1964 when two scientists, Arno Penzias and Robert Wilson, accidentally discovered what is known as the cosmic microwave background radiation. This faint glow of energy spread evenly across the sky was exactly what the Big Bang theory predicted as leftover heat from the birth of the universe. With this discovery, most scientists finally accepted the Big Bang as the best model for explaining how the universe began and evolved. In the late 1960s and early 1970s, brilliant physicists like Roger Penrose, Stephen Hawking, and George Ellis published groundbreaking studies showing that, based on Einstein's theories, the universe must have started from a singularity, a point of infinite density and energy. Then, over the next 2 decades, cosmologists worked hard to refine the Big Bang model and solve lingering mysteries. In the year 1981, physicist Alan Guth introduced the idea of cosmic inflation, a period of incredibly rapid expansion in the early moments of the universe. This concept helped address many puzzles about the structure and uniformity of the cosmos. During this time, 2 major debates kept astronomers busy. One was about the exact value of the Hubble constant, which measures how fast the universe is expanding. The other was about the total amount of matter in the universe, which was thought to determine its ultimate fate. At that time, scientists did not yet know about dark energy, which would later change our understanding of cosmic expansion. Since the late 1990s, there have been incredible advancements in our understanding of the universe, thanks to improvements in telescope technology and space-based observatories. Satellites like the Cosmic Background Explorer, COBE, the Hubble Space Telescope, and the Wilkinson Microwave Anisotropy Probe, WMAP, have provided precise measurements of key features of the universe. Perhaps the most astonishing discovery came when scientists realized that the expansion of the universe is not slowing down, as once thought, but is actually speeding up, an effect now attributed to the mysterious force known as dark energy. Today, the Big Bang theory remains the best explanation for how our universe came to be, and researchers continue to uncover new and exciting details about its origins and ultimate fate. The Big Bang theory provides a detailed explanation for many of the fascinating things we observe in the universe. It helps us understand why certain light elements like hydrogen and helium exist in specific amounts, why we can detect a faint glow called the cosmic microwave background, how galaxies are arranged in massive structures, and why they appear to be moving away from us, as described by Hubble's law. These key pieces of evidence, often called the 4 pillars of the Big Bang model, strongly support the idea that the universe started from a single point and has been expanding ever since. One of the earliest signs that the Big Bang theory was correct came from the discovery that galaxies are moving away from us, which we can tell by looking at the way their light is stretched into longer, redder wavelengths, a phenomenon called redshift. Another major breakthrough was the detection of the cosmic microwave background, a faint signal left over from the early universe. Scientists also confirmed that the proportions of light elements in space match the predictions of a process called Big Bang nucleosynthesis, which explains how these elements formed in the universe's first moments. In recent years, astronomers have gathered even more evidence by studying how galaxies form and how enormous cosmic structures are distributed across space. To fully explain the Big Bang, scientists have proposed some mysterious ideas, including dark matter and dark energy. Dark matter is believed to make up most of the universe's mass, yet we cannot see it directly. We only notice its effects on galaxies and gravity. Many experiments are underway to figure out what dark matter actually is. Dark energy, on the other hand, is thought to be responsible for the universe's rapid expansion, but its true nature remains a mystery. There are also other puzzling questions, such as why small galaxies behave differently than expected and why the centers of galaxies seem to have more dark matter than our models predict. When we look at distant galaxies and quasars, we see that their light has shifted toward the red end of the spectrum. This redshift happens because the universe itself is expanding, stretching the light waves as they travel through space. If we measure how much the light has shifted and compare it to the distance of these objects, we find a clear pattern known as Hubble's law. This law tells us that galaxies farther away from us are moving away faster than those that are closer. The idea that the universe is expanding was first predicted in the early 1920s by scientists like Alexander Friedmann and Georges Lemaitre. It wasn't until 1929 that Edwin Hubble provided real observational proof, changing our understanding of the universe forever. However, there is an unresolved issue known as Hubble tension, which refers to a disagreement between two different methods of measuring how fast the universe is expanding. One method, based on studying the cosmic microwave background, gives a lower number, while another method, based on measuring distances to galaxies, gives a higher number. Scientists are still trying to figure out why these two measurements don't match. One of the biggest discoveries that confirmed the Big Bang theory happened by accident in the year 1964. Two scientists, Arno Penzias and Robert Wilson, were working with a radio antenna when they stumbled upon a mysterious background noise that seemed to come from every direction in space. This turned out to be the cosmic microwave background, leftover heat from the universe's earliest moments. Their discovery matched predictions made by other scientists in the 1950s, tipping the balance of evidence in favor of the Big Bang theory. Because of this, Penzias and Wilson won the Nobel Prize in Physics in 1978. The cosmic microwave background is a faint afterglow from a time when the universe was extremely hot and dense. Back then, space was filled with a thick fog of charged particles, making it impossible for light to travel freely. Around 372,000 years after the Big Bang, these particles combined to form neutral atoms, making the universe transparent for the first time. The light from that moment is what we now see as the cosmic microwave background. In 1989, NASA launched a satellite called COBE, Cosmic Background Explorer, which made two major discoveries. First, in 1990, it confirmed that the cosmic microwave background had a perfect blackbody spectrum, just as predicted. Then, in 1992, it detected tiny temperature variations across the sky, small fluctuations that eventually led to the formation of galaxies and stars. These findings were so important that John Mather and George Smoot received the Nobel Prize in Physics in 2006. Throughout the following years, ground-based and balloon experiments provided even more precise measurements of the cosmic microwave background. In the year 2001, an experiment called Boomerang measured the pattern of these fluctuations and showed that the universe is nearly flat in shape. Then, in 2003, data from the Wilkinson Microwave Anisotropy probe provided the most accurate values yet for key cosmic parameters, helping refine our understanding of the early universe. In May 2009, the European Space Agency launched the Planck space probe, which provided even higher resolution measurements of the cosmic microwave background. Many other experiments, both on Earth and in space, continue to study this radiation, offering deeper insights into the origins and evolution of the universe. Although the Big Bang theory explains a lot, many mysteries remain. Scientists are still trying to understand dark matter, dark energy, and the exact details of what happened in the first moments of the universe. With new technology and ongoing research, we may one day uncover the full story of how our universe began and what its ultimate fate might be. Scientists have used models of the Big Bang to estimate how much of certain light elements, helium, deuterium, a form of hydrogen, and lithium, exist in the universe compared to regular hydrogen. Specifically, they can predict the amounts of helium-4, helium-3, deuterium, and lithium-7. These amounts are determined by one key factor: the ratio of photons, particles of light, to baryons, particles like protons and neutrons. Interestingly, this photon-to-baryon ratio can also be figured out by analyzing tiny temperature variations in the cosmic microwave background, the faint glow left over from the early universe. According to these calculations, helium-4 should make up about 1/4 of the universe's total mass of hydrogen. Deuterium should be about 1/1000th of that mass, helium-3 about 1/10,000th, and lithium-7 an incredibly tiny fraction, about 1/1000th of hydrogen's mass. When astronomers measure the actual amounts of these elements in space, they mostly match what the Big Bang theory predicts. The agreement is particularly strong for deuterium. Helium-4 is slightly different from predictions but still close, while lithium-7 is off by a factor of 2, a discrepancy known as the cosmological lithium problem. Some of this mismatch could be due to measurement uncertainties. Even with these minor differences, the overall agreement between predictions and observations is strong evidence that the Big Bang really happened. This theory remains the only known explanation for why light elements exist in the proportions that they do. In fact, it would be almost impossible for the Big Bang to have produced significantly more or less than between 20 and 30% helium. Without the Big Bang, there's no clear reason why the early universe, before stars even formed, should have contained helium in a greater amount than deuterium, or why these elements should appear in fixed proportions across the cosmos. Scientists have carefully studied the shape and spread of galaxies and quasars, and their findings match what the Big Bang theory predicts. By combining observations with scientific models, they have determined that the first galaxies and quasars started forming within about 1 billion years after the Big Bang. Over time, these cosmic structures have continued to grow, forming enormous clusters of galaxies and even larger superclusters. As the universe has aged, the stars within galaxies have changed and evolved. When astronomers look at galaxies that are very far away, they are actually seeing them as they were billions of years ago in the early universe. These distant galaxies look quite different from those closer to us, which represent a more recent stage of cosmic evolution. Interestingly, galaxies that formed more recently do not look the same as galaxies that formed at similar distances shortly after the Big Bang. This evidence strongly contradicts the old, steady-state theory, which suggested the universe was always the same and had no beginning. Scientists have also found that patterns of star formation, the distribution of galaxies and quasars, and the structure of the universe all align closely with what computer models of the Big Bang predict. These discoveries are helping scientists refine their understanding of how the universe took shape. In the year 2011, astronomers made an extraordinary discovery. By analyzing the light from distant quasars, they found what appeared to be untouched clouds of the very first gases that formed in the universe. Before this, every object ever observed in space contained heavy elements like carbon, oxygen, and silicon, elements that are produced inside stars. However, these two gas clouds had no trace of such elements, suggesting they formed just minutes after the Big Bang, during an event called Big Bang nucleosynthesis. Scientists have also worked out the age of the universe by comparing different methods. One method relies on measuring the universe's expansion rate using the Hubble constant and the cosmic microwave background radiation. Another approach estimates the ages of the oldest stars by studying their life cycles in globular clusters and measuring radioactive elements inside them. Additional evidence comes from studying distant supernovae and analyzing tiny temperature changes in the cosmic microwave background. All these independent measurements point to the same estimated age, which strongly supports the standard cosmological model known as lambda cold dark matter, or the LCDM model. However, some findings have raised questions. One particularly puzzling object, a quasar known as APM 08279 plus 5255, appears to be so complex that some scientists wonder whether it had enough time to form under the LCDM model. Another major prediction of the Big Bang theory is that the cosmic microwave background temperature was higher in the past. Observations of distant gas clouds confirm this idea by showing tiny absorption patterns in their light. This also suggests that a certain cosmic effect, known as the Sunyaev-Zeldovich effect, should remain mostly the same, regardless of how far away a galaxy cluster is. Scientists have observed this to be roughly true, though precise measurements are tricky because galaxy clusters themselves evolve over time. Looking ahead, future gravitational wave observatories might be able to detect ancient gravitational waves. ripples in space-time that could give us a glimpse of the universe less than 1 second after the Big Bang. If scientists succeed, it could be one of the biggest breakthroughs in understanding the origins of our universe. The Big Bang theory has helped scientists understand how the universe began, but it has also raised many puzzling questions. Some of these mysteries have been solved over time, but others remain unanswered. In fact, every time scientists come up with a solution to one problem, it often reveals new mysteries. For example, the horizon problem, the magnetic monopole problem, and the flatness problem are typically explained by the theory of cosmic inflation. However, many details about this inflationary period are still unknown, and some scientists, including those who originally proposed the theory, believe that it has been disproven. One of the biggest unanswered questions is why there is more matter than antimatter in the universe. According to current scientific theories, when the universe was extremely young and incredibly hot, it should have had equal amounts of matter and antimatter. But if this were true, matter and antimatter would have annihilated each other, leaving nothing behind. Instead, the universe we see today is made almost entirely of normal matter. To explain this imbalance, scientists proposed a process called baryogenesis. For baryogenesis to work, 3 specific conditions, known as the Sakharov conditions, must be met. These include the number of baryons, particles like protons and neutrons, must not always be conserved. Certain fundamental symmetries, called C-symmetry and CP symmetry, must be broken. The universe must have moved away from thermal equilibrium at some point. While these conditions can occur in the standard model of physics, they are not strong enough to fully explain why there is so much more matter than antimatter. Scientists are still searching for a complete answer. Observations of exploding stars called Type Ia supernovae have shown that the universe's expansion is not slowing down, it is actually speeding up. This was a shocking discovery, as scientists originally expected gravity to slow the expansion over time. To explain this, researchers proposed the existence of an unknown force or energy called dark energy. Dark energy is believed to make up the majority of the universe's total energy. Scientists studying the faint glow left over from the Big Bang, known as the cosmic microwave background, have found that the universe appears to be almost perfectly flat in shape. According to Einstein's theory of general relativity, this means the total mass and energy of the universe must be very close to a specific value called the critical density. However, when scientists measure the actual amount of matter in the universe, they find that it only accounts for about 30% of the critical density. This means the remaining 70% of the energy must come from something else, dark energy. Dark energy also helps explain the overall shape of the universe by influencing large-scale cosmic structures. It affects the frequency of gravitational lensing when light from distant objects is bent by massive galaxies, and the way sound waves moved through the early universe, leaving patterns known as baryon acoustic oscillations. Although dark energy is the best explanation for these observations, its true nature remains unknown. Some scientists think it may be linked to vacuum energy, while others suggest more exotic possibilities. Data from the Wilkinson Microwave Anisotropy Probe, WMAP, in the year 2008 indicated that the universe is made up of approximately 73% dark energy, 23% dark matter, 4.6% normal matter, less than 1% neutrinos. Interestingly, as the universe expands, the proportion of matter decreases while dark energy remains nearly constant. This means that dark energy will continue to play an increasingly dominant role in the far future. Another major mystery is the existence of dark matter, a type of matter that cannot be seen directly but has a strong gravitational influence on galaxies. In the 1970s and 1980s, astronomers realized that there wasn't enough visible matter in the universe to account for the gravitational forces holding galaxies together. This led to the idea that most of the universe's matter must be invisible. Some estimates suggest that up to 90% of all matter in the universe is dark matter. Without dark matter, many observations don't make sense. For example, galaxies rotate much faster than expected, meaning there must be extra unseen mass holding them together. The large-scale structure of the universe would not have formed in the way we observe it today. The amount of an element called deuterium in the universe is far lower than expected without dark matter. Even though scientists have never directly detected dark matter particles, its presence is inferred through various observations, such as the way galaxies move within clusters, the bending of light due to gravitational lensing, the distribution of hot gas in galaxy clusters, the temperature variations in the cosmic microwave background. Physicists have proposed many possible candidates for dark matter, including exotic particles that do not interact with normal matter except through gravity. Experiments around the world are trying to detect these particles, but so far, none have been found. Despite being the best explanation for many cosmic observations, the dark matter model is not perfect. There are some unexplained problems, including the dwarf galaxy problem. Computer models predict that there should be far more small galaxies than we actually observe. The cuspy halo problem. The centers of galaxies should have a sharp peak in dark matter density, but observations suggest they have a smoother distribution. Some scientists have suggested alternative theories that modify our understanding of gravity instead of requiring dark matter. However, none of these alternatives have been able to explain all observations as successfully as the dark matter model. One of the biggest challenges in modern physics is the so-called cosmological constant problem, sometimes described as the most embarrassing problem in physics. This arises from the fact that the amount of dark energy in the universe, as measured by astronomers, is vastly different from the value predicted by quantum physics. According to calculations based on fundamental physics, the energy density of empty space should be much, much larger than what is actually observed. Scientists have no clear explanation for why the universe's dark energy is so small compared to these predictions. To solve this, some researchers believe that dark energy could be related to Einstein's cosmological constant, a term he originally introduced and later abandoned in his equations. Others suggest more complex ideas, such as quintessence, which proposes that dark energy evolves over time rather than remaining constant. Despite the incredible progress scientists have made in understanding the universe, many mysteries remain. The nature of dark matter and dark energy, the imbalance between matter and antimatter, and the strange acceleration of the universe's expansion are all problems that astrophysicists are still trying to solve. Each new discovery brings us closer to answering these questions, but at the same time, it often opens the door to even deeper mysteries. The quest to unravel the secrets of the cosmos continues, and the answers may reshape our understanding of the universe in ways we cannot yet imagine. The horizon problem comes from a simple but mind-bending idea. Nothing, not even information, can move faster than light. Since the universe has only been around for a limited amount of time, this means that only certain regions of space could have ever interacted with each other. The boundary that marks how far any kind of influence could have traveled is called the particle horizon. Here's where the problem arises. When we look at the cosmic microwave background, CMB, the faint glow left over from the early universe, it looks almost exactly the same in every direction. But if the universe had always been filled with just radiation and matter, as scientists once thought, then regions separated by more than about 2 degrees in the sky should never have had the chance to exchange heat or energy. So how did they all end up with the same temperature? The solution to this mystery comes from a revolutionary idea called inflation theory. This theory suggests that at an incredibly early stage, long before atoms or even basic particles like protons and neutrons existed, the universe was dominated by a strange, uniform energy field. During this period, the universe expanded at an exponential rate, growing unimaginably fast. Because of this rapid expansion, regions that today seem impossibly far apart were actually close together before inflation began. That means they could have interacted and balanced out their temperatures before being flung apart by inflation. This explains why the CMB appears so smooth and uniform across the sky. There's another fascinating consequence of inflation: quantum fluctuations, tiny, random energy blips predicted by Heisenberg's uncertainty principle, got stretched to enormous scales. These fluctuations became the seeds of the galaxies, stars, and cosmic structures we see today. Inflation predicts that these early variations were almost perfectly balanced, and modern measurements of the CMB confirm this prediction. While inflation explains a lot, it raises another tricky question. According to most models, inflation ended long before the electroweak epoch, the time when fundamental forces like electromagnetism and the weak nuclear force split into separate forces. If distant parts of the universe were already cut off from each other by then, why don't we see major irregularities in the universe today? This remains an open question in cosmology. Back in the 1970s, physicists working on grand unified theories, GUTS, predicted the existence of magnetic monopoles, particles that act like isolated north or south poles of a magnet. These objects should have formed in huge numbers in the early, high-energy universe. But after decades of searching, no one has found a single one. Inflation solves this mystery in a simple way. It stretched the universe so much that any monopoles that did exist were spread out to such an extreme degree that they became practically undetectable. Another puzzling feature of the universe is its flatness. Space can be positively curved, like a sphere, negatively curved, like a saddle, or flat, like a piece of paper. The shape depends on the universe's total energy density. If the density had been even slightly off in the past, the universe would have either collapsed long ago or expanded into a nearly empty void. Yet, after billions of years, it still appears remarkably flat. To put this into perspective, at the time of nucleosynthesis, when the first atomic nuclei formed just a few minutes after the Big Bang, the density of the universe had to be within 1 part in 10 quadrillion of the critical value to prevent a runaway collapse or endless expansion. That level of precision is hard to explain unless some mechanism actively forced the universe toward flatness. Inflation provides the answer again. Just as a rapidly expanding balloon smooths out wrinkles on its surface, the extreme stretching of space during inflation drove the universe toward flatness, ensuring that we live in a cosmos that still looks balanced today. Many people mistakenly believe that the Big Bang theory explains how everything, including time, space, and energy, came into existence. However, that is not quite true. The Big Bang theory does not tell us what caused the universe to exist. Rather, it describes how the universe we see today grew from an extremely small, incredibly hot, and dense state. A common mistake is imagining the Big Bang as a small object suddenly expanding, like a balloon being blown up. But when scientists talk about the size of the universe at the time of the Big Bang, they are referring only to the observable universe, the part of the universe we can see. The entire universe may be much larger, or possibly even infinite, and we may never fully know its true scale. Another misconception is thinking of the Big Bang as an explosion, where matter was thrown apart like shrapnel from a bomb. In reality, what happened was the expansion of space itself, like a stretching fabric, carrying galaxies along with it. Some scientists describe this process as the expansion of space, while others describe it as objects moving apart. Both explanations can be correct depending on how you look at it. According to Hubble's law, the farther away a galaxy is, the faster it seems to be moving away from us. Some galaxies appear to be moving faster than the speed of light. But this does not mean they are actually breaking the laws of physics. Instead, space itself is stretching, making the distances between galaxies grow faster over time. This is different from the way objects move within space. Many people have heard that the redshift of distant galaxies is caused by the expansion of space. While this is partly true, the most straightforward explanation is something called the Doppler effect, the same effect that makes a passing ambulance sound different as it moves toward or away from you. In this case, as light travels across the universe, it gets stretched into longer wavelengths, shifting toward the red part of the spectrum. Scientists can make predictions about what will happen to the universe, but only for a limited time, although that limit is far longer than the current age of the universe. Beyond that, things become much more uncertain. Similarly, while scientists have learned a great deal about the universe's early moments, the true origin of everything remains unknown. When the Big Bang first happened, the universe was unimaginably hot and dense. The Belgian scientist Georges Lemaitre referred to this starting point as the primeval atom, while another scientist, George Gamow, used the term ILM to describe the dense material that made up the early universe. We still do not know exactly how or why this initial state came into existence. However, the Big Bang theory does give us some clues about how the universe developed afterward. Scientists have also proposed that our universe is stable because of the way physical laws work. Some theories suggest that there could be an infinite number of universes, and only the ones with the right conditions could develop life. But what happened before the Big Bang? This is one of the biggest mysteries in physics. The Big Bang theory is based on Einstein's general relativity, but at extremely high temperatures, this theory breaks down. To truly understand the earliest moments of the universe, scientists need a theory that combines gravity and quantum mechanics, something known as quantum gravity. Some theories suggest that time itself might not have existed before the Big Bang, meaning that asking what happened before might not even make sense. While we do not have definitive answers, scientists have come up with several fascinating ideas about what might have happened before or during the Big Bang. Quantum fluctuation model. This idea suggests that the Big Bang was caused by a sudden, random fluctuation in a quantum field. Even though it seems extremely unlikely, in an infinite amount of time, even the most improbable events can eventually happen. The emergent universe. Some theories describe the universe as existing forever in a low-energy state before suddenly transitioning into an expanding state, much like ancient myths about the universe being born from a cosmic egg. The no-boundary model, proposed by Stephen Hawking and James Hartley, this theory suggests that the universe did not have a beginning in the traditional sense. Instead of a singular point, time and space smoothly emerge from a finite past. Brain cosmology. Based on string theory, this idea suggests that our universe exists on a giant brain, a higher dimensional surface, and the Big Bang may have been triggered by a collision with another brain. Cyclic universe. This theory proposes that the universe does not have a true beginning or end, but instead expands and contracts in an endless cycle. The Big Bang could have been the result of a previous universe collapsing. Eternal inflation and the multiverse. According to this idea, different parts of the universe may expand at different rates, creating bubble universes. Our universe could be just one bubble among many in a much larger multiverse. While scientists have learned an incredible amount about the Big Bang, many questions remain unanswered. Future discoveries in quantum physics, gravity, and cosmology may eventually reveal what happened in those first unimaginable moments, or even before. Until then, the story of the universe remains one of the greatest mysteries of all time. Before scientists discovered dark energy, they had two main ideas about how the universe might end. The first idea was that if the universe had too much mass, its gravity would eventually slow down its expansion and pull everything back together. Over billions of years, the universe would stop growing, shrink, and get hotter and denser until it collapsed into an incredibly compact and fiery state, just like it was at the very beginning. This scenario is known as the Big Crunch. The second idea was that if the universe had just the right amount of mass, or even less, it would keep expanding forever, though more and more slowly. Over time, stars would burn through all the available gas in galaxies, meaning no new stars could form. The stars that remained would eventually burn out, leaving behind cold, dead remnants like white dwarfs, neutron stars, and black holes. These objects would collide and merge, forming larger black holes. Meanwhile, the universe would continue cooling down, with its temperature gradually approaching absolute zero, a state known as the Big Freeze. If protons, the building blocks of atoms, are unstable, then all ordinary matter would eventually decay, leaving behind nothing but radiation and black holes. Over unimaginable stretches of time, even black holes would vanish as they slowly release energy through Hawking radiation. At this point, the universe would have reached heat death, meaning all useful energy would be gone and nothing could happen anymore. However, modern discoveries show that the universe isn't just expanding. It's actually expanding faster and faster because of a mysterious force called dark energy. This means that more and more galaxies will eventually move so far away from us that we will never be able to see or interact with them again. Scientists still don't know exactly how this will end, but one widely accepted idea, called the LCDM model, suggests that galaxies and other structures held together by gravity will remain intact while everything else gets colder and more isolated, leading to heat death. There's another, more dramatic possibility, known as the Big Rip. If dark energy becomes stronger over time, it could eventually tear apart everything. Not just galaxies and stars, but even planets, atoms, and the tiniest building blocks of matter. In this case, the universe wouldn't just fade into stillness, it would be ripped apart completely. Beyond science, the Big Bang, the event that started the universe, has sparked deep discussions in religion and philosophy. Some see it as evidence of a divine creator, while others believe it eliminates the need for one. This debate has made the Big Bang one of the most fascinating intersections between science and spirituality. When we think about the origins of the universe, we often imagine an empty void before everything came into existence. But modern physics tells a different story, one that challenges our deepest understanding of reality. Instead of a cold, lifeless nothingness, what we once thought of as empty space is actually an invisible, buzzing realm filled with energy and mysterious activity. This leads us into the fascinating world of quantum mechanics, a branch of physics that explores how the universe works at the smallest possible scales. At the heart of quantum mechanics is a shocking discovery. Space, even when stripped of all matter and light, is never truly empty. Instead, it is alive with what scientists call quantum fluctuations, tiny, unpredictable bursts of energy that appear and disappear in an instant. These fluctuations are not just random events, they are the foundation of some of the most mind-boggling discoveries in modern science. They might even hold the answer to one of the biggest mysteries of all. How did the universe begin? For thousands of years, humans believed that if you removed everything from a space, every atom, every particle, every bit of light, you would be left with true emptiness. This idea of nothingness was widely accepted by scientists and philosophers alike. However, breakthroughs in quantum physics in the past century have completely overturned this assumption. In reality, what appears to be empty space is far from empty. Instead, it is a restless sea of energy, constantly shifting and changing due to the effects of quantum fluctuations. These fluctuations occur because of something known as the uncertainty principle, a key idea in quantum mechanics introduced by the physicist Werner Heisenberg. This principle states that at a fundamental level, we can never precisely know both the position and speed of a particle at the same time. This unavoidable uncertainty leads to a strange consequence. Even in what we perceive as a vacuum, energy constantly flickers in and out of existence. This chaotic and unpredictable activity creates what scientists call quantum foam, an invisible, churning sea of energy at the smallest levels of reality. Even though we cannot see it with the naked eye, its effects can be measured and have been experimentally proven. The first solid evidence that empty space contains energy came in 1947, thanks to two Dutch physicists named Hendrik Casimir and Dirk Polder. They conducted a simple but groundbreaking experiment that revealed one of the strangest forces in the universe, now called the Casimir effect. In their experiment, Casimir and Polder placed two small, flat metal plates extremely close together inside a vacuum, a place where, according to classical physics, there should be nothing at all. If space were truly empty, then nothing should have happened. But to their amazement, the plates moved toward each other as if an invisible force was pulling them together. At first, this seemed impossible. What could be causing this mysterious attraction between the plates? The answer lay in the quantum fluctuations of space itself. Even in a vacuum, energy fluctuations occur all around the plates. However, because the plates were positioned very close to each other, they restricted the types of fluctuations that could exist between them. Meanwhile, the space outside the plates still had all possible quantum fluctuations happening freely. This imbalance in quantum energy created pressure, pushing the plates together. This discovery was revolutionary. It proved that what we thought was nothing was actually full of invisible energy. The Casimir effect provided direct experimental evidence that quantum fluctuations were real and that even an apparent vacuum is never truly empty. Now, this is where things get even more incredible. If the empty space of the universe is filled with these tiny bursts of energy, could they have played a role in the birth of the universe itself? Many physicists believe the answer is yes. According to some of the most widely accepted theories in modern cosmology, the entire universe may have been born from a quantum fluctuation in a primordial vacuum. Think of it like this. Instead of the universe emerging from absolute nothingness, it might have come from a state where energy was already present, hidden beneath the surface, waiting for the right moment. Under the right conditions, one of these quantum fluctuations could have suddenly expanded, triggering what we now call the Big Bang. This idea is supported by quantum field theory and cosmic inflation, which suggest that the universe underwent an incredibly rapid expansion in its earliest moments. Instead of a universe emerging from a void of true nothingness, it may have burst forth from a quantum vacuum, a place where energy and fluctuations were already bubbling beneath the surface. Even after the Big Bang, quantum fluctuations continued to play a crucial role in shaping the cosmos. Immediately after the universe came into existence, it was an unimaginably hot and energetic place. During this time, quantum fluctuations acted like tiny seeds in the fabric of space. At first, these fluctuations were incredibly small, almost imperceptible. However, as the universe expanded, these tiny variations in energy spread out over vast distances. Over billions of years, these minuscule differences in energy and density grew under the influence of gravity. Slowly but surely, these fluctuations became the foundation for galaxies, stars, and planets. Without them, the universe might have remained a perfectly smooth and featureless expanse, and life as we know it may never have formed. The theory of cosmic inflation, first proposed by physicist Alan Guth, explains how these quantum fluctuations were stretched to enormous scales in the early universe. This rapid expansion magnified the microscopic variations in energy, turning them into the large-scale structures we observe in the universe today. The idea that quantum fluctuations could give rise to an entire universe is both thrilling and unsettling. If our universe emerged from a quantum fluctuation, could it be just one of many? Some physicists believe that our universe is just one of countless others that may have formed in a similar way. This leads to the multiverse hypothesis, which suggests that quantum fluctuations could be continuously spawning new universes, each with its own unique properties and laws of physics. In this view, what we consider reality might just be a tiny part of a much larger cosmic landscape, with universes popping into existence and disappearing all the time. The discovery of quantum fluctuations has shattered the traditional notion of nothingness. It reveals that even in the most barren regions of space, there is a hidden, restless energy at work, one that may have given birth to the cosmos itself. Even more astonishing is the idea that the universe may not require a traditional cause to exist. In our everyday world, everything happens for a reason. Every effect must have a cause. But in the bizarre and unpredictable world of quantum mechanics, things can happen spontaneously, without any apparent reason. Particles can pop in and out of existence. Energy can appear and disappear in an instant. And under the right conditions, a single quantum fluctuation might have created the universe as we know it. This challenges everything we think we know about existence. If the universe could arise from quantum fluctuations, does that mean reality itself is built on randomness? The idea that our entire universe might have sprung from an almost imperceptible ripple in the fabric of quantum energy is both astonishing and mind-expanding. It challenges everything we think we know about existence and forces us to confront one of the deepest mysteries of all time. How did the universe create itself? Quantum mechanics, the branch of science that studies the tiniest building blocks of reality, provides a surprising answer. It suggests that what we think of as nothing isn't truly empty. Instead, it is an invisible, ever-changing space filled with potential energy, constantly shifting in ways we cannot see. Imagine a cosmic stage where unseen forces are always at work. Tiny bursts of energy flickering in and out of existence like sparks. These fleeting fluctuations may seem insignificant, but under the right conditions, they could act as the first sparks that ignite the birth of something far greater, perhaps even an entire universe. Scientists have long explored this mind-bending possibility through quantum field theory, a framework that attempts to explain how these mysterious energy shifts operate. However, this field of study is still in its early stages, and many questions remain unanswered. How exactly could these quantum fluctuations have led to the vast and structured universe we see today? What forces guided this transformation from chaos to order? The truth is, we are only beginning to scratch the surface of these cosmic secrets. Yet, the notion that our universe could have emerged from an invisible, quantum-fueled phenomenon reshapes our understanding of creation itself. It offers a daring and unconventional perspective, one where the cosmos may have been born not from an external force or divine command, but from the strange and powerful properties of space itself. While much remains unknown, one thing is clear. The deeper we explore, the more we realize that reality is far stranger, more complex, and more incredible than we ever imagined. This new way of looking at how the universe began changes everything we once believed about existence. Instead of thinking of creation as a single moment that happened billions of years ago, we now see it as an ongoing process, a never-ending cycle of birth and destruction that plays out in the hidden world of quantum physics. In this strange and mysterious realm, the difference between nothing and something is not as simple as we once thought. In fact, what appears to be empty space is not truly empty at all. It is filled with invisible energy, just waiting for the right conditions to bring something new into existence. With this perspective, the birth of our universe was not a one-time event, but part of an endless rhythm of creation. Imagine an unseen cosmic dance, where the potential for new worlds is present in every single moment. What scientists call the quantum vacuum, often thought of as a vast, empty void, is actually a restless sea of energy, constantly bubbling with activity. Even the tiniest shifts in energy can trigger the birth of entire galaxies, stars, and planets. In the study of the universe, there is a fascinating idea called cosmic inflation, also known as cosmological inflation or simply inflation. This theory suggests that in the very first moments of existence, the universe expanded at an incredibly fast rate, far faster than it does today. Imagine a tiny dot, suddenly stretching into something millions and millions of times larger in the blink of an eye. This happened right after the Big Bang, creating the foundation for everything we see today. After this rapid inflation ended, the universe kept expanding, but at a much slower pace. Then, something even stranger happened. More than 7,700,000,000 years after the universe was born, about 5,400,000,000 years ago, this expansion started to speed up again. Scientists believe this is because of a mysterious force called dark energy, which is still not fully understood. The idea of cosmic inflation was developed between the late 1970s and the early 1980s. Several brilliant physicists contributed to it, including Alexei Starobinsky from the Landau Institute for Theoretical Physics, Alan Guth from Cornell University, and Andrei Linde from the Lebedev Physical Institute. Their work was so groundbreaking that in 2014 they were awarded the Kavli Prize for pioneering this theory. But why is inflation important? One of the biggest mysteries in cosmology is how the large-scale structure of the universe, such as galaxies, clusters of galaxies, and cosmic voids, came to be. Inflation provides a possible answer. Tiny quantum fluctuations, which are microscopic changes in energy during this inflationary period, got stretched to enormous sizes. Over time, these fluctuations became the seeds from which galaxies and other cosmic structures formed. Physicists also believe that inflation explains other puzzling aspects of the universe. It helps us understand why the universe looks nearly the same in every direction, why the cosmic microwave background radiation is evenly spread, why the universe appears to be flat, and why scientists have never found strange particles called magnetic monopoles, which some theories predicted should exist. Even though the idea of cosmic inflation is widely accepted, scientists still do not know exactly what caused it. Some theories suggest that a special kind of field, called the inflaton field, was responsible. The inflaton could have created a force that made space expand faster than the speed of light for a brief moment before slowing down. Many predictions of inflation have been supported by scientific observations. For example, in 1992, the COBE satellite detected tiny temperature differences in cosmic microwave background radiation, just as inflation theory predicted. Later, the WMAP satellite provided even stronger evidence. However, not every scientist agrees, and some researchers still question whether inflation truly happened. The idea that the universe is expanding goes back to the early 1930s, when astronomer Edwin Hubble made a groundbreaking discovery. He found that light coming from faraway galaxies was redshifted, meaning that the galaxies were moving away from us. Even more interestingly, the farther a galaxy was, the faster it was receding. This meant that the universe was not static, it was stretching and growing. However, before Hubble's discovery, two scientists, Alexander Friedmann and Georges Lemaitre, had already predicted that the universe should be expanding based on Einstein's general theory of relativity. They suggested that an initial powerful push had sent everything flying outward, and gravity had never been strong enough to stop it. Cosmic inflation might be the missing piece of this puzzle. According to Friedmann's equations, a special kind of energy with negative pressure could cause a powerful repulsion effect, making space expand exponentially fast. This kind of energy could have come from a quantum field in a false vacuum state, a state where energy is temporarily trapped at a higher level before settling down. In 1979, physicist Alan Guth introduced the idea that this inflationary expansion could also explain why certain exotic particles, like magnetic monopoles, have never been found. Inflation would have spread them out so much that they became incredibly rare, solving a major problem in physics at the time. Scientists also realized that inflation solves two other major mysteries. The horizon problem. How is it possible that regions of the universe that are billions of light-years apart look so similar? Inflation suggests they were once much closer together before expanding rapidly. The flatness problem. Why does space seem to have a perfectly flat geometry rather than being curved? Inflation explains that the rapid expansion stretched out any curvature, making the universe appear flat. Imagine looking out at the night sky and knowing that there is a limit to how far you can see, not because of any physical barrier, but because the universe itself is expanding. Just like standing on Earth and seeing the horizon where the land seems to meet the sky, the universe has its own horizon, called the cosmological horizon. This marks the farthest distance from which light has had time to reach us since the beginning of the universe. However, beyond this limit, space is stretching so fast that light from those regions will never reach us. The part of the universe we can observe is just a small patch of a much larger cosmos. There are regions so far away that they have never had a chance to send any light or signals toward Earth. These hidden regions are beyond our current cosmological horizon, which scientists estimate is about 46 billion light-years away in all directions. In the traditional view of the Big Bang, without adding extra theories, the cosmological horizon expands over time, revealing new regions of space. But here's a puzzling problem. Whenever we see a new region for the first time, it looks almost identical to all the others. Its background radiation, which is a faint glow left over from the Big Bang, has nearly the same temperature as all other regions. Its space-time curvature, or the way gravity bends space, is also in sync with the rest of the universe. How is this possible? How did these regions know what temperature and curvature to have when they were never in contact before? This is where the theory of inflation comes in. Inflation suggests that, in the very early universe, space expanded at an incredibly fast, almost unimaginable rate due to a powerful energy field, sometimes called vacuum energy or a cosmological constant. Unlike normal expansion, this process kept the cosmological horizon at a fixed distance. This means that regions of space were rapidly pushed apart from each other, preventing them from communicating. But because they all started from the same small, uniform space, they carried the same temperature and curvature even after being stretched out across the cosmos. As inflation slowed down and the special energy field faded, the universe switched to a more gradual expansion. The regions that inflation had pushed beyond our view slowly came back into sight, appearing just as they had before, maintaining their nearly identical temperatures and curvatures. This explains why the universe looks so uniform, even in places that were never in contact. The theory of inflation makes another fascinating prediction. It suggests that the overall shape of the universe should be perfectly flat, meaning the total amount of normal matter, dark matter, and residual energy in space must add up to a precise value known as the critical density. Observations confirm that this is indeed the case. Inflation also helps scientists predict tiny variations in temperature across the sky, caused by small quantum fluctuations that occur during this rapid expansion. Many of these predictions have been tested and confirmed, adding strong support to the theory. In a universe that expands at an accelerating rate, objects that start off near each other will gradually drift apart faster and faster, unless they are held together by some force, like gravity. From the perspective of one object, the surrounding space behaves similarly to a black hole turned inside out. Anything that crosses a certain boundary, its personal event horizon, can never return, and even light signals from it will never reach back. This kind of exponentially expanding space is known as de Sitter space. For it to exist, there must be a special energy known as the cosmological constant, which remains constant over time and prevents space from slowing down. When space expands at exactly an exponential rate, this vacuum energy creates a type of pressure that perfectly balances its energy density. However, in most inflationary models, the expansion isn't perfectly exponential. It's slightly slower, meaning the horizon grows gradually over time as the vacuum energy slowly decreases. This slight difference allows scientists to make precise predictions about how inflation shaped the early universe, many of which align with what we observe today. When the universe was very young, it went through a rapid period of expansion called inflation. One of the most important effects of this expansion was that it stretched out any differences in temperature or density that might have existed, making everything much more uniform. Essentially, inflation smoothed out any irregularities, making the universe nearly identical in every direction and reducing any natural curvature it may have had. At this stage, the universe was almost entirely controlled by a mysterious force field known as the inflation field. The only small differences left were tiny quantum fluctuations, minute variations that later played a role in forming galaxies and other structures. Another consequence of inflation was that it greatly reduced the number of exotic heavy particles, such as magnetic monopoles, rare particles predicted by certain physics theories. If the universe had ever been hot enough to create these particles before inflation began, they would have become so spread out that finding even one today would be extremely unlikely. Scientists refer to these effects as the no-hair theorem of inflation, a concept borrowed from black hole physics. The basic idea is that just like black holes eventually lose all distinguishing features except for their mass, charge, and spin. The universe after inflation lost almost all traces of its earlier complexity, leaving behind a simple, smooth, and nearly empty state. Inflation caused the universe to expand by an enormous amount in a very short time. As space expanded, the density of most forms of energy decreased because they became more spread out. For example, the density of ordinary matter, like dust, dropped by a factor of 8 when the universe doubled in size. Radiation, such as light, lost energy even faster because in addition to spreading out, its wavelengths also stretched, causing what is known as redshift. When the universe doubled in size, the energy density of radiation dropped by a factor of 16. However, during inflation, the inflation field maintained a nearly constant energy level. Meanwhile, everything else, irregularities, curvature, exotic particles, and even normal particles, had their energy diluted so much that they became insignificant. This left the universe extremely uniform, flat, and mostly empty by the time inflation ended. Inflation was a period of extreme cooling. The temperature dropped by an astonishing factor of 100,000. In the earliest models of inflation, scientists estimated that the temperature fell from about 10 to the power of 27 Kelvin to around 10 to the power of 22 Kelvin. This freezing phase continued throughout inflation. However, once inflation ended, the universe's temperature shot back up. This process is called reheating or thermalization, as the enormous energy stored in the inflation field transformed into normal particles, like those that make up atoms, and electromagnetic radiation. This marked the beginning of the universe's radiation-dominated era. Even though inflation theory explains many things about the early universe, there are still mysteries. Scientists do not fully understand what the inflation field is made of or exactly how reheating happened. However, some believe it occurred through a process known as parametric resonance, in which energy was transferred in a highly efficient and rapid manner. Back in the 1970s, scientists found several puzzling issues with the Big Bang theory. To solve these mysteries, physicist Alan Guth came up with the idea of cosmic inflation in 1979. His research began with a simple question. Why don't we see magnetic monopoles, hypothetical particles that should exist according to some physics theories? Guth discovered that if space contained a special kind of energy called a false vacuum, it would trigger an incredibly rapid expansion, an exponential stretching of space itself. Very quickly, scientists realized this could explain not just the magnetic monopole problem, but also other deep mysteries of the universe. These mysteries all pointed to one strange fact. For the universe to look the way it does today, it had to start in a very precise, fine-tuned state. Inflation provides a way for the universe to naturally reach this state, making a cosmos like ours much more likely under the Big Bang theory. One of the biggest puzzles in cosmology is called the horizon problem. This problem asks, Why does the universe look so uniform, with galaxies spread out evenly and the cosmic background radiation having almost the same temperature everywhere? To understand this, imagine a canister of gas. The gas inside spreads out evenly because the molecules have had time to mix and balance their temperature. But the early universe did not have enough time to mix in this way. In the standard Big Bang model without inflation, regions of space that are very far apart today were always too far apart to interact. They were moving away from each other faster than the speed of light, meaning they could never exchange heat or information. This makes it difficult to explain why they ended up with nearly identical temperatures. Scientists had tried other explanations before inflation. Georges Lemaitre and Richard Tolman suggested that the universe might have gone through multiple cycles of expansion and contraction, allowing it to reach thermal balance over time. However, their ideas ran into a problem: entropy buildup. With each cycle, disorder would increase, making their models unworkable. Another attempt came from physicist Charles Misner, who proposed a chaotic early universe, something called the Mixmaster model, that might have naturally smoothed things out. But later studies showed this wouldn't actually solve the problem. Inflation, on the other hand, provides a simple and elegant answer. It proposes that before the universe became the size we see today, it underwent a period of extreme, rapid expansion. This means that regions of space that are now billions of light years apart were once right next to each other. They had time to interact, balance out their temperatures, and then got stretched far apart. This is why the universe appears so uniform today. Another mystery is called the flatness problem. When astronomers look at the universe, they find that space is almost perfectly flat, meaning its overall shape follows Euclidean geometry, the kind of geometry you learn in school, where parallel lines stay parallel and angles of a triangle always add up to 180 degrees. This is strange because, over time, space curvature should have grown much more noticeable. The density of matter in the universe is extremely close to the critical density, the precise amount needed for space to remain flat rather than curving into a sphere or a saddle shape. However, in a universe without inflation, if we rewind time, this fine balance becomes more and more extreme. At the moment of the Big Bang nucleosynthesis, when the first atoms formed, the curvature had to be 1 part in 10 quadrillion. That's 16 zeros. Any slight deviation from this balance in the early universe would have resulted in a universe that either expanded too fast, preventing galaxies from forming, or collapsed in on itself. Inflation solves this by stretching space so rapidly that any initial curvature gets smoothed out, just like how blowing up a balloon makes its surface appear flatter. This explains why space today is so close to perfectly flat. According to a set of physics ideas called Grand Unified Theories, GUTS, the forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force were once combined into one single force in the very early universe. When the universe cooled down, this force split apart, like ice forming from water. But these theories also predict the creation of magnetic monopoles, particles that carry a one-sided magnetic charge, like a magnet that has only a north pole or only a south pole. These should have been created in enormous numbers in the early universe. If that were the case, they would be everywhere today, and yet we have never found even one. Inflation offers a simple solution. If the universe expanded dramatically right after these particles formed, it would have spread them so far apart that they would be incredibly rare today, too few to detect. In other words, inflation diluted them out of existence. However, some scientists, including Martin Rees, have pointed out a humorous issue with this explanation. He noted that skeptics might say, "It's easy to claim success in preventing a problem when the problem itself might never have existed in the first place." Regardless, inflation remains the best explanation for why we don't see these exotic particles today. In the early days of general relativity, Albert Einstein introduced a mathematical term called the cosmological constant. He did this to make the universe appear static and unchanging, as many scientists at the time believed it was. His model described the universe as a three-dimensional sphere filled evenly with matter. However, Dutch physicist Willem de Sitter later discovered a completely different solution, one where the universe was expanding rapidly due to the cosmological constant, but otherwise contained no matter at all. Scientists later realized that Einstein's model was unstable. If even the smallest disturbance occurred, it would either collapse or transform into a rapidly expanding de Sitter universe. Fast forward to the mid-1960s, a physicist named Erast Gleiner came up with a groundbreaking idea. He suggested that in the early universe, pressure wasn't behaving the way scientists expected. Instead of pushing outward, the pressure was actually negative and directly tied to energy density. This idea, though largely unnoticed at the time, would later become the first theoretical clue pointing toward dark energy, the mysterious force that makes up most of our universe today. By the early 1970s, a problem with the Big Bang theory started to emerge. The Soviet physicist Yakov Zeldovich noticed two major issues: the flatness problem, why the universe's overall shape appears nearly perfectly flat instead of curved, and the horizon problem, why distant regions of the universe look so similar despite being too far apart to have ever interacted. Up until then, scientists assumed the universe's smoothness was just a lucky coincidence. In the Soviet Union, these puzzles led two physicists, Vladimir Belinsky and Isaac Kalatnikov, to study a chaotic mathematical concept known as the BKL singularity, a potential explanation for the disorderly early moments of the universe. Meanwhile, in the United States, physicist Charles Misner developed the Mix-Master universe, a model that used chaotic motion to try to solve these cosmic mysteries, though with only limited success. Then came the late 1970s, when physicists turned to quantum mechanics to understand how the universe might have started. Sidney Coleman, an American theoretical physicist, used a mathematical technique called instantons, developed by Alexander Polyakov and others, to explore how unstable states in quantum fields might suddenly switch to more stable ones. He realized that much like water needs a tiny ice crystal to begin freezing, the universe might have needed a tiny bubble of true vacuum to trigger its expansion. However, Coleman didn't fully explore the role of gravity in this process, or its connection to the evolution of the cosmos. One of the boldest ideas in physics suggests that the universe might have emerged from nothing, with no space, no time, and no matter. This would have happened due to quantum fluctuations, tiny energy shifts that can spontaneously create particles. In 1978 and 1979, three physicists, Robert Brute, François Englert, and Edgard Gunzig, proposed that our universe might have begun as a random fluctuation in empty space, followed by a phase where it expanded like a de Sitter universe before transitioning into the familiar expanding universe we observe today. Their idea was groundbreaking because it suggested the universe had no absolute beginning in the traditional sense. At the same time, another Soviet scientist, Alexei Starobinsky, proposed that quantum effects could play a crucial role in the early universe. He argued that when space-time is curved enough, quantum mechanics naturally produces something similar to a cosmological constant, leading to an inflationary phase where the universe expands exponentially. His model not only solved the problems raised by Zeldovich, but also made predictions about subtle changes in the cosmic microwave background, the faint afterglow of the Big Bang. Around 1978, Zeldovich identified another major puzzle, the magnetic monopole problem. This was a more precise version of the horizon problem, but it applied specifically to particle physics. It suggested that there should be an abundance of strange, single-pole magnets in the universe, but none had ever been found. In 1980, physicist Alan Guth realized that rapid inflation of the early universe could explain why we don't see these magnetic monopoles. His idea was that the universe, as it cooled down from the Big Bang, got stuck in a high-energy state, similar to how supercooled water can stay liquid below its freezing point. Eventually, this unstable state broke apart, triggering a rapid, exponential expansion known as inflation. At nearly the same time, another physicist, Demosthenes Kazanis, suggested that inflation could solve the horizon problem, while Katsuhiko Sato proposed that it could also get rid of exotic structures called domain walls. In 1981, Einhorn and Sato expanded on Guth's idea, demonstrating that it not only explained the lack of magnetic monopoles, but also other cosmic puzzles. However, their models required an extremely fine-tuned cosmological constant, and the rapid expansion could have made the universe too clumpy, leading to extreme density variations. Guth further developed his inflationary model, arguing that the early universe, as it cooled, was trapped in a state of false vacuum, a condition with high energy density similar to the cosmological constant Einstein once proposed. Eventually, bubbles of true vacuum formed, rapidly expanding at the speed of light and consuming the false vacuum. However, Guth soon realized a major flaw. His model didn't explain how the universe became filled with the heat and radiation we observe today. The process of bubble formation wasn't enough to reheat the universe properly. For inflation to fully work, something had to generate radiation, and in his original model, this could only happen if bubbles collided. But if inflation lasted long enough to solve the initial problems, then bubbles would be so far apart that they wouldn't collide often enough. A major challenge in early inflationary models, known as the bubble collision problem, was finally solved by André Linde and separately by Andreas Albrecht and Paul Steinhardt. They introduced a new approach called new inflation or slow-roll inflation, which improved upon the earlier model developed by Alan Guth, now referred to as old inflation. In Guth's original idea, inflation involved a sudden tunneling from a false vacuum state, but this led to issues with the formation of bubbles that would collide in an inconsistent way. The new inflation model worked differently. Instead of abrupt tunneling, it proposed that inflation was driven by a scalar field rolling slowly down an energy landscape, much like a ball rolling down a hill. As long as the slope was gentle, the universe expanded at an exponential rate. However, as the slope steepened, inflation came to an end and a process called reheating took place, allowing energy to convert into matter and radiation, setting the stage for the formation of the universe as we know it. Over time, scientists discovered that new inflation did not create a perfectly smooth and symmetrical universe. Instead, tiny quantum fluctuations appeared in the inflaton field. These minute irregularities acted as the seeds for the formation of galaxies, stars, and all cosmic structures we see today. The first calculations of these fluctuations were made by Vyacheslav Mukhanov and G.V. Chibisov, while studying a similar model proposed by Alexei Starobinsky. In the early 1980s, researchers working independently at the Nuffield Workshop on the Very Early Universe, held at Cambridge University, also analyzed these fluctuations. The event, which lasted for 3 weeks in the year 1982, brought together several leading physicists who arrived at the same conclusion about quantum fluctuations in inflation. Stephen Hawking, Alexei Starobinsky, Alan Guth with So Young Pi, and a team consisting of James Bardeen, Paul Steinhardt, and Michael Turner, each worked separately to confirm the existence of these primordial fluctuations. Despite these early challenges, inflationary theory has since been refined, evolving into one of the most accepted explanations for how our universe came to be. Scientists continue to test and refine these ideas, using cosmic observations to uncover the true origins of space and time itself. The idea of cosmic inflation is a key part of modern cosmology. It helps explain why the universe looks the way it does, why it appears uniform in all directions, and why space seems so flat. This concept also solves some puzzling questions, such as why we don't see certain strange particles, like magnetic monopoles, which theories predict should exist. Since physicist Alan Guth first introduced the idea of inflation in the late 20th century, Scientists have gathered more evidence to support it, with one of the strongest confirmations coming from the Planck spacecraft study of the cosmic microwave background. These observations show that the universe is incredibly flat, with a margin of error of just 0.5%. They also confirm that the universe's structure is almost perfectly uniform, with tiny variations occurring only once in every 100,000 regions. Inflation theory suggests that the galaxies, stars, and other large structures we see today formed from tiny fluctuations in energy that existed in the early universe. These fluctuations, which appeared due to quantum mechanics, later grew larger due to gravity. Scientists describe these fluctuations as a nearly scale-invariant Gaussian random field, which means that they follow a specific pattern predicted by inflation. This pattern depends on just two key numbers, one that sets the overall strength of the fluctuations, and another that slightly adjusts the pattern from a perfectly uniform state. Another important prediction of inflation is something called the tensor-to-scalar ratio, which describes the amount of gravitational waves present compared to the fluctuations in energy. Simple inflation models suggest this ratio should be close to 1/10. Another key aspect of inflation theory is that all these early fluctuations should have been in balance with one another, a condition known as thermal equilibrium. Observations from multiple space missions, including Planck and the Wilkinson Microwave Anisotropy Probe, WMAP, as well as galaxy surveys like the Sloan Digital Sky Survey, have confirmed this prediction. These studies show that the tiny irregularities in the cosmic microwave background match the expectations from inflation almost exactly. Scientists have also measured the spectral index, a number that tells us how much the fluctuations deviate from a perfect balance. If the universe had a perfect balance, this index would be exactly 1. The simplest inflation models predict a value between 92 hundredths and 98 hundredths, and data from the Planck mission suggests a value of about 97 hundredths. This is considered strong evidence for inflation. Over time, researchers have developed various versions of inflation theory, each making slightly different predictions. However, most require a lot of fine-tuning, meaning their parameters must be adjusted very precisely to match observations. Despite this, inflation remains valuable because it can predict the starting conditions of the universe with just two key numbers, the spectral index and the fluctuation amplitude. These predictions hold true regardless of the exact way inflation might have happened. Sometimes, new observations seem to challenge inflation theory. For example, early data from the WMAP mission hinted that the fluctuations might not be as uniform as expected. However, later data showed this was likely just a statistical anomaly. Another unexpected finding came from studies of the cosmic microwave background, which showed that some fluctuations were lined up with the plane of the solar system, something that scientists did not expect. Some researchers have suggested this could be a sign of new physics, quantum effects, or even biases in how the data is analyzed. Scientists continue to test inflation theory with more precise measurements. One major focus is on detecting B modes, a pattern in the polarization of the cosmic microwave background that could provide direct evidence of gravitational waves from inflation. In March of the year 2014, a team using the BICEP-2 telescope announced they had found these B modes, suggesting strong evidence for inflation. They estimated a tensor-to-scalar ratio between 15 hundredths and 27 hundredths. However, by June of that year, their confidence in the result decreased, and by January of the year 2015, doubts grew even stronger. By the year 2018, new data indicated that the actual ratio was at most 6 hundredths, meaning that the earlier detection might have been a false signal. Other upcoming experiments could further test inflation. The Planck spacecraft might provide additional clues, but it is unclear if the signals will be strong enough to detect. Another promising approach is studying 21-centimeter radiation, which comes from neutral hydrogen before the first stars formed. This method could give an even clearer picture of the universe's early structure. However, challenges remain. such as interference from radio signals on Earth and in space, which might make the measurements difficult. When Alan Guth first introduced his idea of cosmic inflation, some scientists thought that the inflaton, the field responsible for inflation, was actually the Higgs field. The Higgs field is what gives mass to elementary particles. However, more recent studies suggest that this might not be true. One of the main problems with this idea is that it doesn't fully align with experimental data from studies of particle physics, especially at the electroweak scale. Because of this, many scientists started looking for other explanations. Some turned to grand unified theories, GUTs, which attempt to unify the fundamental forces of nature to find a better model for inflation. One of the biggest challenges with inflation theory is something called fine-tuning. This means that for inflation to happen, the conditions have to be extremely precise. In the new inflation model, a concept called slow roll conditions must be met. These conditions require the inflaton field to have a very smooth and gentle potential compared to the enormous vacuum energy of the universe. The inflaton particles also need to have a very small mass. For inflation to work under this model, the universe must have a special kind of scalar field with an extremely flat potential, as well as carefully arranged starting conditions. Scientists have proposed explanations for why this might be the case. One possible explanation involves scale-invariant field theories. In these theories, a property called scale invariance, which means the equations look the same at any scale, is broken by tiny quantum effects. This could explain why the inflationary field has such a flat potential. However, this explanation only works if the theory can be studied using a mathematical approach called perturbation theory. Physicist Andre Linde introduced a different idea known as chaotic inflation. He proposed that inflation isn't something that requires extremely specific conditions. Instead, he argued that inflation could naturally happen in almost any universe that starts in a chaotic, high-energy state with a scalar field that has unlimited potential energy. In this theory, the inflaton field takes on values greater than 1 Planck unit, the smallest meaningful unit in physics. This is why these models are often called large field models, while competing models, such as new inflation, are referred to as small field models. However, this idea presents its own problems. According to effective field theory, if the inflaton field reaches such large values, the theory's predictions might no longer hold. This is because a process called renormalization, used to keep calculations in quantum field theory from giving infinite or meaningless results, could introduce large corrections that disrupt inflation. Scientists still haven't solved this issue, and some argue that small field models, where inflation happens at a much lower energy scale, provide a better explanation. While inflation depends heavily on quantum field theory and an approximation of quantum gravity, it has not yet been fully integrated with these theories. Physicist Robert Brandenberger pointed out another fine-tuning issue. The size of the tiny ripples in the universe that eventually became galaxies and clusters of galaxies is directly linked to the energy scale at which inflation happened. This energy scale is estimated to be around 10 quadrillion, 10 to the power of 16, giga-electron volts, which is roughly 1,000th of the Planck energy. The problem is that the natural energy scale in physics is typically the Planck scale, which is much higher. The fact that inflation occurs at a much lower energy level is sometimes seen as another kind of fine-tuning, known as the hierarchy problem. However, this is not usually considered a major flaw because the energy scale of inflation matches naturally with the scale at which fundamental forces might unify. Many models suggest that inflation never fully stops across the entire universe. Instead, it continues indefinitely in at least some regions. This happens because parts of the universe that are inflating grow so quickly that they keep producing new inflating regions. If the transition from inflation to a normal, non-inflating state is too slow, then new inflating regions will appear faster than old ones disappear. In such models, most of the universe's volume at any given time is still inflating, meaning that inflation never truly ends on a cosmic scale. This leads to a fascinating consequence: an infinite and ever-growing multiverse. The idea of a multiverse has sparked intense debate among scientists. Some believe it is a natural outcome of inflation, while others argue that it undermines the entire theory. Physicist Paul Steinhardt, one of the original minds behind inflation theory, was also the first to propose the concept of eternal inflation in the early 1980s. He suggested that once inflation begins, it can go on forever. He described how bubbles of non-inflating space, filled with hot matter and radiation, could form within the inflating universe. However, these bubbles would not grow fast enough to take over, so inflation would continue in the surrounding empty space. Later in the same decade, Alexander Vilenkin demonstrated that eternal inflation is a general feature of many inflationary models, meaning it would happen under a wide range of conditions. In new inflation models, the inflaton field is expected to roll down its potential, much like a ball rolling down a hill. However, due to tiny quantum fluctuations, it can sometimes randomly jump back up, creating new inflating regions. Since these higher energy regions expand much faster than lower energy ones, they tend to dominate the overall volume of the universe. This means that in any model where the inflaton field has no upper limit, inflation will continue indefinitely. However, there is a mathematical problem with this idea. While inflationary space behaves similarly to de Sitter space, a model of an expanding universe, it cannot stretch infinitely into the past. There must have been a starting point. Unlike de Sitter space, an inflating universe would eventually collapse into a singularity, a point of infinite density. Because of this, scientists still need a solid theory to explain how the universe began in the first place. In eternal inflation, the inflating regions of the universe grow exponentially, while non-inflating regions do not. This means that the inflating part of the universe is always far larger than the parts that have stopped inflating. However, inflation eventually ends in certain regions, allowing galaxies, stars, and planets to form. One of the biggest debates in modern physics is how to assign probabilities to different regions of this hypothetical multiverse. Some scientists argue that since inflation keeps going in most of the universe, we should expect it never to end. Others suggest that if we assume a local observer, such as ourselves, must exist to see the universe, inflation must eventually stop. Some physicists believe that the paradox of eternal inflation can be solved by considering how much space existed before inflation began. Others argue that this paradox is a fundamental flaw in inflation theory. Interestingly, Paul Steinhardt, who originally helped develop the idea of eternal inflation, later became one of its harshest critics for this reason. Some scientists have tried to get around the challenge of explaining how the universe began by suggesting that it never had a beginning at all. Instead, they propose that the universe has always existed, continues to exist, and will never stop existing. According to these ideas, the universe is infinitely large and has been expanding at an ever-increasing rate forever. Other theories suggest that the universe came into existence from nothing, based on ideas from quantum physics and cosmic inflation. One such idea was introduced by physicist Alexander Vilenkin, while Stephen Hawking and James Hartley proposed a different concept called the no-boundary idea. Their model suggests that the universe naturally went through inflation right after it appeared, without needing a specific starting point. Physicist Alan Guth described cosmic inflation as the ultimate free lunch. He suggested that new universes, much like our own, are constantly forming within a vast, ever-expanding cosmic background. In this scenario, gravity plays a unique role. It bends the usual rules of physics, but does not break them. Normally, physics dictates that energy must be conserved and that disorder, or entropy, must always increase. However, Guth's idea suggests that gravity allows for an exception, creating new universes without violating these fundamental laws. Despite this, some scientists remain skeptical. One of them, Don Page, argued that inflation might not actually solve the problem of the universe's initial conditions. Instead, he believed it made things more complicated. According to him, for the universe to follow the rules of thermodynamics, it would have needed to start in an extremely organized, low-entropy state, a situation that is highly unlikely. If inflation did happen, it would have increased entropy even more, meaning the universe's original state would have needed to be even more orderly than traditional Big Bang models suggest. This paradox led some to question whether inflation really explains the universe's beginning or just makes the mystery deeper. Later, when Hawking and Page tried to calculate how likely it was for inflation to have happened, they got unclear results. Some scientists argue that this doesn't matter because once inflation begins, it continues indefinitely. As long as the chance of inflation happening is not exactly zero, it would eventually dominate and take over the universe. Others, like physicists Andreas Albrecht and Lorenzo Sorbo, claimed that an inflationary universe was far more likely than one without inflation. They reasoned that inflation requires much less initial energy to get started compared to an alternative model where inflation never happens, making it the more probable scenario. Another challenge, known as the trans-Planckian problem, arises from the fact that inflation occurred at energy levels not far from the smallest possible scale in physics, the Planck scale. Some scientists argue that before inflation, quantum fluctuations in space were so small that they were below the Planck length. If this is true, then unknown laws of quantum gravity might have affected how the early universe formed. The impact of this is still debated. Some believe these effects are too small to measure, while others think they could be significant. A variation of inflation, called hybrid inflation, builds on an earlier theory known as new inflation. It introduces additional energy fields, where one field controls the universe's expansion and another determines when inflation stops. In this model, inflation doesn't continue forever. Instead, after lasting long enough, one of these fields reaches a state where it suddenly causes inflation to end, allowing the universe to continue evolving in a new phase. This concept of inflation is somewhat similar to the mysterious force known as dark energy, which is currently making the universe expand at an accelerating rate. However, dark energy operates at a much lower energy level, roughly 10 to the power of -12 gigaelectron volts, which is about 27 orders of magnitude lower than the energy level at which inflation occurred. A major breakthrough came with the discovery of flux compactifications, which helped link inflation to string theory. One version of this idea, known as brane inflation, suggests that inflation happens when special objects in string theory, called d-branes, move through extra dimensions. These branes interact with anti-d branes, triggering inflation in a way that is different from traditional models. However, scientists still don't fully understand how this process works. It seems that inflation in this scenario happens through a process similar to old inflation, where the universe moves from one state to another by quantum tunneling. After that, another mechanism must take over to complete inflation. Another approach comes from a field called loop quantum gravity, which suggests that space itself is made up of tiny, discrete units. In this theory, if the energy of the universe ever becomes too high for this quantized space to contain it, the universe could bounce instead of collapsing, potentially providing an alternative explanation for how inflation began. While these theories explore different possibilities, they all attempt to answer one of the biggest questions in science. How did the universe begin, and what forces shaped its evolution? Scientists have put forward different ideas to explain the mysteries of the early universe, and some of these theories offer alternatives to the widely accepted concept of cosmic inflation. One such idea is the Big Bounce hypothesis, which suggests that instead of the universe beginning from an infinitely small and dense point, a singularity, it actually went through a period of contraction before suddenly expanding again. This bounce provides an explanation for the conditions that led to the Big Bang. It naturally solves two major puzzles in cosmology: the flatness problem, why the universe appears so uniform and smooth on large scales, and the horizon problem, why different regions of the universe, which should never have been in contact, have similar properties. This explanation is found within a modified version of Einstein's theory of gravity, known as the Einstein-Cartan-Siyama-Kibble theory. Unlike standard general relativity, this theory introduces an extra factor called torsion, which affects how particles interact in extreme conditions. In simple terms, when the universe was incredibly dense, torsion created a force that prevented it from collapsing into an infinitely small point. Instead of a singularity, there was a minimum size before the universe bounced back into expansion. This early, rapid expansion explains why the universe today looks flat, smooth, and uniform on the largest scales. As time passed and the universe became less dense, the effects of torsion faded, leading to the universe entering the radiation-dominated phase we observe in early cosmic history. Another set of theories, called ekpyrotic and cyclic models, offer a different explanation. These models propose that the universe goes through endless cycles of expansion and contraction. Long before the Big Bang, the universe was already expanding, which helps explain the horizon problem. Then, during a contracting phase, the universe collapses into a big crunch, only to be reborn again in a hot Big Bang phase. This cycle continues indefinitely. These models resemble an older idea from the early 20th century called the oscillatory universe, proposed by Richard Chase Tolman. However, unlike Tolman's version, which suggested the universe had a finite lifespan, modern cyclic models allow for an eternal universe with no beginning or end. One challenge for these models is whether they can properly explain the small density variations in the early universe that later formed galaxies. There is also debate about whether the universe can successfully transition between the Big Crunch and Big Bang without breaking known physical laws. A potential advantage of these models is that they avoid the magnetic monopole problem, an issue in physics where certain predicted particles have never been observed. This only works as long as the temperature at the Big Crunch remains below a critical level, known as the Grand Unified Scale, which is needed to create these missing particles. If the cyclic model is correct, we wouldn't yet see evidence of the universe slowing down, since each cycle is expected to last about 1 trillion years. Another alternative to inflation comes from string theory, which suggests that, besides the 3 dimensions of space we experience, additional hidden dimensions exist. These extra dimensions are thought to be extremely small and curled up, making them unnoticeable in everyday life. This idea appears in supergravity models and other theories trying to unify quantum mechanics and gravity. A concept called string gas cosmology, proposed by Robert Brandenberger and Kumrun Vafa, tries to explain why only 3 dimensions became large while the others remained compact. Their theory imagines the early universe as a hot gas filled with tiny, vibrating strings, the fundamental building blocks of nature according to string theory. These strings can wrap around extra dimensions, and for a dimension to expand, the strings that are wrapped around it must be able to cancel each other out. Their calculations suggest that this process works best in exactly 3 large spatial dimensions, which matches what we observe today. Scientists are still working on refining this idea, especially to see if it can explain the small variations in matter that led to galaxies forming. The original version of the theory did not fully solve some key cosmological problems, but later improvements incorporating the bouncing universe idea have addressed these issues. Yet another proposal challenges a fundamental law of physics, the speed of light. Some researchers suggest that in the very early universe, light traveled much faster than it does today. This is known as the variable speed of light, VSL theory. If true, it would mean that different parts of the universe could have exchanged information and energy more easily, solving the horizon problem without needing inflation. In this model, as the universe evolved, the speed of light gradually slowed down to the value we observe today. These alternative theories provide fascinating possibilities for understanding the origins of the universe. While none have yet replaced inflation as the leading explanation, ongoing research continues to explore whether any of them might provide a better fit for the cosmic puzzle. For as long as humans have gazed up at the night sky, one big question has always lingered in their minds. Are we truly alone? Is Earth the only place in this vast, endless universe where life can exist? Or could there be other worlds, hidden among the stars, where living creatures thrive, just like us? This mystery has fascinated philosophers, scientists, and dreamers for thousands of years. It is a question that challenges everything we think we know about life, space, and the very nature of existence itself. Now, thanks to incredibly powerful telescopes and groundbreaking scientific advancements, we are closer than ever to uncovering the truth. The search for life beyond Earth, known as the hunt for extraterrestrial life, is one of the most exciting and important quests in modern science. It takes us far beyond the reaches of our own solar system to distant exoplanets, planets that orbit stars light years away from the Sun. It also forces us to look at our own solar system in new ways, exploring its hidden corners for signs of life. As scientists push deeper into this great mystery, they are also redefining what life is and what it truly means to be alive. One of the biggest questions scientists are trying to answer is, what makes a planet capable of supporting life? Earth is full of life in every form imaginable, from the tiniest bacteria to towering trees and enormous ocean creatures. But why is our planet so special? What conditions make life possible here, and could those same conditions exist on other planets? A key ingredient for life, at least as we understand it, is liquid water. Every living thing on Earth needs water to survive. It helps dissolve substances, making it possible for chemical reactions to take place. Water also carries nutrients, helps maintain stable temperatures, and supports the basic structures inside cells. Without water, life as we know it simply could not exist. But why does Earth have liquid water while other planets do not? The answer lies in Earth's unique position in space. Our planet sits in a very special region around the Sun called the habitable zone. This is the perfect distance where temperatures are just right, not too hot and not too cold, allowing water to remain in liquid form. Planets that are too close to their stars, like Venus, are so hot that any water on their surface boils away. Planets that are too far, like Mars, are so cold that water turns to ice. But Earth sits in the perfect spot, allowing lakes, rivers, and oceans to exist, making life possible. However, water alone is not enough. Life also needs an energy source. On Earth, the main source of energy is the sun. Plants use sunlight to create food through a process called photosynthesis. In turn, animals eat plants or other animals to get the energy they need to survive. The sun's energy drives every aspect of life, from the tiniest plants to the mightiest predators. But what if life could survive without sunlight? Scientists have discovered that deep in Earth's oceans, far beyond the reach of the sun, strange creatures thrive near hydrothermal vents. These are openings on the ocean floor that release heat and chemicals from beneath the Earth's crust. The organisms living there do not rely on sunlight at all. Instead, they use the heat and chemicals from these vents to create energy, proving that life can exist in conditions far different from those on Earth's surface. This discovery has completely changed how we think about life in the universe. If life can survive in such extreme environments on Earth, could it also exist on distant planets or moons under similar conditions? Some scientists believe that places like Europa, a moon of Jupiter, or Enceladus, a moon of Saturn, could be home to alien life. These icy moons are believed to have vast oceans hidden beneath their frozen surfaces. If heat from their cores provides energy, just like hydrothermal vents do on Earth, then perhaps life could be thriving in those dark, alien waters. But for life to develop and evolve over time, it needs more than just water and energy. It needs stability. A planet or moon must have the right conditions for millions or even billions of years for life to take hold and grow. Think of it like planting a tree. If the soil, sunlight, and water keep changing too much, the tree won't survive. In the same way, Earth has remained stable long enough for life to flourish. But what about other worlds? Could they also provide the right conditions for life to evolve? The search for life beyond Earth is not just about finding alien creatures. It is about understanding our place in the universe. If we discover even the tiniest microbe on another planet, it would change everything. It would prove that life is not unique to Earth, that the universe is teeming with possibilities, and that somewhere, far beyond the stars, we may not be alone after all. One of the most crucial gifts Earth provides to all living things is its atmosphere. This invisible shield that surrounds our planet plays several vital roles. First, it protects us from harmful radiation coming from space, which would otherwise be deadly. Second, it helps maintain a stable climate by trapping heat and preventing extreme temperature swings. Third, it acts as a barrier against powerful solar winds that could strip away our planet's surface. Without this protective layer, Earth would be an icy, barren wasteland constantly bombarded by deadly radiation, an environment where life as we know it could not survive. Now, imagine what it would take for another planet to sustain life. For a world to support living creatures, it would need an atmosphere that shields against cosmic radiation, a way to regulate temperature so it doesn't become too hot or too cold, and a strong magnetic field to deflect harmful solar winds. These are the same features that make Earth habitable. Without them, any planet would be left vulnerable to harsh space conditions, making it nearly impossible for life to thrive. This brings us to a fascinating question. How many planets out there have the same life-friendly conditions as Earth? Could there be other worlds where life has emerged and evolved just as it did here? To explore this, scientists turn to a concept known as the Drake equation. This mathematical formula, created by astronomer Frank Drake in the year 1961, is designed to estimate how many intelligent civilizations in our galaxy might be capable of communicating with us. Rather than providing a direct answer, the equation helps break down the problem into smaller, more manageable parts, each one addressing a different factor that could influence the existence of extraterrestrial life. The Drake equation considers several key questions. For example, how many stars in our galaxy have planets? Out of those, how many planets have the right conditions for life to develop? Among those, how many might give rise to intelligent beings? And, of the planets with intelligent life, how many civilizations would advance far enough to create technology that allows them to send signals across space? Even though the Drake equation doesn't give us a definite answer, it serves as a roadmap, helping scientists organize their search for alien life. It reminds us that many complex factors must align for a civilization to exist and become detectable. But here's the big mystery. If life is common in the universe, why haven't we heard from anyone yet? This puzzling question is known as the Fermi paradox. We know that the conditions for life might exist beyond Earth, and yet, despite years of searching, we have found no signs of other civilizations. Scientists and thinkers across the world continue to debate this enigma. Where is everyone? If intelligent beings are out there, why haven't they reached out? In the year 1950, physicist Enrico Fermi famously asked, "Where is everybody?" His question was based on a simple but powerful observation. If the universe is so vast and filled with countless stars and planets, and if intelligent life is likely, then why haven't we detected any extraterrestrial civilizations? This contradiction between the high probability of life existing elsewhere and the complete lack of evidence is what we now call the Fermi paradox. The paradox forces us to confront an unsettling reality. With billions of planets scattered throughout the universe, it seems reasonable to expect that at least some should host intelligent beings. And yet, despite our best efforts, we have found no messages, no radio signals, and no traces of advanced alien societies. The silence is deafening. There are many possible explanations for this mystery, but none are proven. One possibility is that intelligent civilizations are extremely rare, making it almost impossible to find them. Another theory suggests that while life may be common, very few species ever develop advanced technology. Perhaps most civilizations destroy themselves before they reach a stage where they can communicate across space, whether through war, environmental collapse, or other catastrophic events. One of the most crucial gifts Earth provides to all living things is its atmosphere. This invisible shield that surrounds our planet plays several vital roles. First, it protects us from harmful radiation coming from space, which would otherwise be deadly. Second, it helps maintain a stable climate by trapping heat and preventing extreme temperature swings. Third, it acts as a barrier against powerful solar winds that could strip away our planet's surface. Without this protective layer, Earth would be an icy, barren wasteland, constantly bombarded by deadly radiation, an environment where life as we know it could not survive. Now, imagine what it would take for another planet to sustain life. For a world to support living creatures, it would need an atmosphere that shields against cosmic radiation, a way to regulate temperature so it doesn't become too hot or too cold, and a strong magnetic field to deflect harmful solar winds. These are the same features that make Earth habitable. Without them, any planet would be left vulnerable to harsh space conditions, making it nearly impossible for life to thrive. This brings us to a fascinating question. How many planets out there have the same life-friendly conditions as Earth? Could there be other worlds where life has emerged and evolved just as it did here? To explore this, scientists turn to a concept known as the Drake equation. This mathematical formula, created by astronomer Frank Drake in the year 1961, is designed to estimate how many intelligent civilizations in our galaxy might be capable of communicating with us. Rather than providing a direct answer, the equation helps break down the problem into smaller, more manageable parts, each one addressing a different factor that could influence the existence of extraterrestrial life. The Drake equation considers several key questions. For example, how many stars in our galaxy have planets? Out of those, how many planets have the right conditions for life to develop? Among those, how many might give rise to intelligent beings? And, of the planets with intelligent life, how many civilizations would advance far enough to create technology that allows them to send signals across space? Even though the Drake equation doesn't give us a definite answer, it serves as a roadmap, helping scientists organize their search for alien life. It reminds us that many complex factors must align for a civilization to exist and become detectable. But here's the big mystery. If life is common in the universe, why haven't we heard from anyone yet? This puzzling question is known as the Fermi paradox. We know that the conditions for life might exist beyond Earth, and yet, despite years of searching, we have found no signs of other civilizations. Scientists and thinkers across the world continue to debate this enigma. Where is everyone? If intelligent beings are out there, why haven't they reached out? In the year 1950, physicist Enrico Fermi famously asked, "Where is everybody?" His question was based on a simple but powerful observation. If the universe is so vast and filled with countless stars and planets, and if intelligent life is likely, then why haven't we detected any extraterrestrial civilizations? This contradiction between the high probability of life existing elsewhere and the complete lack of evidence is what we now call the Fermi paradox. The paradox forces us to confront an unsettling reality. With billions of planets scattered throughout the universe, it seems reasonable to expect that at least some should host intelligent beings. And yet, despite our best efforts, we have found no messages, no radio signals, and no traces of advanced alien societies. The silence is deafening. There are many possible explanations for this mystery, but none are proven. One possibility is that intelligent civilizations are extremely rare, making it almost impossible to find them. Another theory suggests that while life may be common, very few species ever develop advanced technology. Perhaps most civilizations destroy themselves before they reach a stage where they can communicate across space, whether through war, environmental collapse, or other catastrophic events. For many years, scientists have been searching for signs of intelligent life beyond Earth. Some experts believe that these advanced civilizations might be so incredibly far away that their signals haven't reached us yet. Others suggest that the vast distances between us make it nearly impossible for us to detect them. Another possibility is that these civilizations are deliberately avoiding us, perhaps for their own safety, ethical reasons, or simply because they have no interest in making contact with a species that is less technologically advanced. Even with these challenges, the search for extraterrestrial life continues. Scientists remain hopeful that one day we will find undeniable proof that we are not alone in the universe. If we were to discover intelligent alien life, it would be one of the most astonishing and history-changing moments of all time. It would completely transform our understanding of the universe and redefine our place within it. Even though we haven't yet found aliens, our journey to uncover the truth has already led to incredible discoveries about the cosmos and even about our own existence. This search for alien life is not limited to one country or a small group of researchers. It is a worldwide effort. Scientists from all over the globe are working together, using some of the most advanced technology available to scan the skies for any signs of extraterrestrial intelligence. One of the main tools used in this search is the radio telescope. These enormous instruments are designed to detect very specific signals, known as narrowband radio signals. These signals are extremely precise and focused, making them unlikely to come from natural sources like stars or planets. Instead, they could be a sign of an advanced civilization trying to communicate across space. While no confirmed alien signals have been detected yet, scientists are not giving up. They continue to improve their equipment, making it more sensitive and capable of scanning larger portions of the sky, increasing the chances of finding something remarkable. But the search for extraterrestrial life isn't just about listening for signals. It also involves finding planets beyond our solar system that might support life. Space missions like Kepler and TESS have helped astronomers discover thousands of exoplanets, revealing that planets are far more common in the universe than we ever imagined. In fact, there are likely more planets than stars in our own galaxy. Some of these exoplanets are located in what scientists call the habitable zone, a region around a star where conditions might be just right for liquid water to exist. Since water is essential for life as we know it, planets in this zone are considered the most promising candidates for hosting alien life. Every new discovery brings scientists closer to identifying a planet with the right conditions for life. But while we search the distant corners of the universe, there are also fascinating possibilities much closer to home. Some of the best places to look for alien life might not be on faraway planets, but on moons right here in our own solar system. Two of the most intriguing locations for potential alien life are Europa and Enceladus, moons of Jupiter and Saturn, respectively. At first glance, these frozen worlds might seem lifeless and uninviting. However, beneath their thick layers of ice, scientists believe there are vast oceans of liquid water. These hidden oceans could provide the perfect environment for life to exist, even in extreme conditions. Water is one of the most important ingredients for life, and these subsurface oceans might have all the necessary conditions to support living organisms. Europa, in particular, has captured the interest of scientists for many years. NASA is preparing to launch the Europa Clipper mission in the near future, which will study the Moon in great detail. This spacecraft will look for signs of life beneath Europa's icy surface by analyzing its ocean, ice, and other features. Scientists are especially curious to see if the conditions on Europa are similar to deep-sea environments on Earth, where strange and resilient creatures thrive without sunlight. Enceladus is another exciting candidate for hosting life. In the year 2005, NASA's Cassini spacecraft made a groundbreaking discovery. It found that Enceladus was spewing huge plumes of water vapor into space. These plumes suggest that there is a vast liquid ocean beneath the ice, and they might contain the chemicals necessary for life. If tiny microorganisms exist in these hidden waters, it would be an incredible breakthrough, proving that life can exist beyond Earth. What makes these icy moons so fascinating is that they could help us understand how life might survive in the most extreme environments. If life can thrive in the dark, hidden oceans of Europa or Enceladus, then it's possible that similar conditions exist on other moons or planets throughout the universe. This could completely change how we think about the search for alien life, leading us to look beyond just Earth-like planets and consider entirely new possibilities. The search for life beyond Earth is one of the most thrilling and profound challenges humanity has ever faced. It forces us to question everything we know about life, the universe, and our own existence. Are we truly alone in the cosmos, or is there something or someone out there waiting to be discovered? Every time we detect a strange signal, find a new planet, or uncover evidence of a hidden ocean, we take one step closer to answering that ultimate question. Long before modern scientists tried to explain the mysteries of the universe, ancient thinkers were already asking profound and puzzling questions. What does it truly mean to exist? And is it even possible for there to be such a thing as nothing, a state of absolute emptiness? One of the earliest philosophers to explore this mind-boggling idea was Parmenides, who lived in ancient Greece over 2,400 years ago. He had a bold and fascinating belief: true nothingness could never exist. To him, the very concept was a contradiction. If something truly did not exist, how could we even think about it, let alone describe it? He argued that existence has no beginning and no end. It has always been there and will always be there. According to Parmenides, the universe was never created. It simply exists, unchanging and eternal. His reasoning was simple yet astonishing. If there had ever been a time when absolutely nothing existed, then nothing could have ever come into existence. Because from nothing, nothing can come. His perspective forces us to rethink everything we assume about reality. If true nothingness is impossible, does that mean the universe has existed in some form forever? But not everyone agreed with Parmenides. Even in his time, other great minds struggled with this paradox. One of them was Aristotle, who lived about 100 years after Parmenides. He had a very different view. Aristotle did not see nothingness as an impossible contradiction. Instead, he saw it as a kind of potential, a blank space where new things could emerge. Imagine an empty canvas before an artist starts painting. To Aristotle, this emptiness was not truly nothing. It was filled with possibilities, a foundation for creation. Even if a space seemed empty, he believed it still contained the potential for things to exist. For centuries, philosophers and scientists have debated these ideas. Can true nothingness ever exist? If the universe somehow came from nothing, what kind of nothing could that be? These questions push the limits of human thought, challenging everything we think we know about reality itself. Fast forward over 2,000 years, and a new thinker, Immanuel Kant, took this mystery even further. He lived in the 18th century and questioned whether the human mind was even capable of understanding nothingness. He raised a deep and unsettling idea. Perhaps true nothingness, the complete absence of everything, is beyond what our brains can even comprehend. After all, our entire existence is based on a world full of things: matter, space, time, things we can touch and measure. But Kant argued that absolute nothingness, where there is not even empty space, is so foreign to human experience that we might not even be able to imagine it. This leads to an even bigger question. Does absolute nothingness even exist at all? Or is what we call nothing actually the very thing that gives rise to everything around us, the invisible force that sparks creation itself? These are the kinds of questions that have fascinated some of the greatest minds in history, ultimately leading to one of the biggest mysteries of all: the birth of the universe. If we jump ahead a few thousand years to modern times, our understanding of nothingness has changed dramatically. While philosophers were lost in deep thought about this paradox, scientists were taking a different approach. Instead of just debating ideas, they were using tools like mathematics and experiments to uncover the secrets of the universe. And what they discovered turned everything we thought we knew about nothingness upside down. For centuries, scientists believed that space, the vast, dark emptiness beyond Earth, was exactly that: empty. A vacuum, they thought, was a place where there was no matter, no energy, just an endless void where nothing happened. If you removed all the air from a space, leaving behind a perfect vacuum, it was assumed that absolutely nothing would remain. But in the 20th century, everything changed. In the early 1900s, Albert Einstein introduced the groundbreaking theory of general relativity, which completely transformed our understanding of space. He showed that space and time were not separate things, but were actually connected, forming a kind of flexible fabric that could bend and stretch in response to matter and energy. This was a revolutionary idea. It meant that space was not just an empty stage where events happened. Instead, space itself was an active and dynamic force that could shape the universe. But the real shock came with the rise of quantum mechanics, the branch of physics that studies the tiniest building blocks of reality. Scientists discovered something astonishing. Even in the emptiest parts of space, where nothing should exist, something was still happening. At the smallest scales, empty space was not truly empty. It was alive with invisible activity, filled with strange, fleeting bursts of energy and particles appearing and disappearing in an instant. What scientists once thought of as nothing turned out to be far more mysterious and complex than anyone had imagined. And with that realization, the ancient question remained: is there truly such a thing as nothing? Or is nothingness simply another way of describing something we do not yet fully understand? Imagine a completely empty space, a place with no matter, no light, and nothing we usually think of as something. But even in this seemingly empty space, things are still happening. It's not loud or obvious, but it's always there. This strange activity is called quantum fluctuations, tiny bursts of energy that appear for a moment and then disappear just as quickly. It's as if, on the smallest scale, the universe is always buzzing with movement, even when it seems completely still. These quantum fluctuations happen so fast and are so small that we can't see them with our eyes. But even though we can't directly see them, we can measure their effects. They are real and can be studied. It turns out that even in what looks like empty space, invisible forces are still at work. These forces behave like waves in the ocean, creating tiny particles that appear and vanish in an instant. These particles are called virtual particles, and even though they exist for a very short time, they leave behind proof that they were there. The idea that empty space is full of activity might sound strange or even magical. After all, how can something happen in a place with nothing in it? But this is the surprising truth of the quantum world. Things never fully stop moving. Even in complete emptiness, something is always shifting, changing, and appearing for just a moment before fading away. Now, this leads to a fascinating question. Could this constant activity of energy and particles be the reason everything exists? Could the entire universe have started from one of these tiny bursts of energy, appearing out of nowhere and then growing into the vast universe we see today? This is one of the most mind-blowing ideas in science. If quantum fluctuations can create small bursts of energy in empty space, could they also explain how the whole universe came from what seems like nothing? It's a question that takes us deep into the mystery of where everything began, challenging everything we thought we knew about nothing and everything. What if the universe we live in started because of a huge, sudden event on a cosmic scale? This brings us to a theory that has fascinated scientists for years: the Big Bang. It was the moment when everything, space, time, and matter, suddenly came into being. But the big mystery is what caused this explosion? What could have set off such an enormous event that created everything in existence? One of the most amazing ideas comes from the strange world of quantum physics. This theory suggests that the universe might have started from what scientists call a vacuum fluctuation. Imagine for a moment a vast empty space. No stars, no planets, no galaxies, just nothingness. And then, out of nowhere, a tiny burst of energy appears. At first, it's incredibly small, but it grows rapidly, expanding and forming everything around us. Stars, galaxies, planets, and even the very space we exist in. This idea suggests that the universe didn't come from true nothingness. It came from a quantum event, a sudden fluctuation that emerged from what we once thought was empty space. Before the Big Bang, this nothingness wasn't as empty as we imagined. Instead, it was filled with quantum potential, just waiting for something to trigger it. It was like hidden energy, a cosmic seed, waiting to grow into the vast universe we see today. As strange as this idea might sound, it is based on some of the most advanced scientific research. Famous physicists like Stephen Hawking and Lawrence Krauss have explored this very idea. Their studies suggest that the unusual laws of physics, especially quantum mechanics and gravity, might actually allow the universe to come from nothing without breaking any scientific rules. Stephen Hawking's work on how the universe began suggested that space and time could come from what's called a quantum state. In this view, the universe didn't need a creator or a guiding force to shape it as traditional religions describe. Instead, the universe could have made itself, simply following the rules of quantum physics. It's as if the universe naturally unfolded based on the laws that control the tiniest particles, without needing anything outside of those rules to start it. Lawrence Krauss built on this idea in his book A Universe from Nothing. He took it even further, suggesting that quantum fluctuations, the tiny random movements that happen in empty space, could actually create entire universes. Just like how tiny particles suddenly appear and disappear in empty space, our entire universe could have come from one of these fluctuations. From this point of view, the universe may have begun through an amazing and unlikely event where nothing turned into everything we see today. The idea of nothing has always been a big mystery that has fascinated both philosophers and scientists. For centuries, people thought of nothing as just an empty, lifeless space, simply a blank area where there was no matter, no energy, and nothing happening at all. However, the idea of nothing is actually much more complicated and surprising than it seems. In philosophy, thinkers have long discussed the idea of potential. This idea suggests that even in what looks like nothing, there is hidden potential waiting to appear. It's almost as if nothing isn't truly empty. Rather, it's a space full of possibilities. In science, this idea becomes even more exciting. Through quantum physics, we now know that even the emptiest space is actually full of tiny bursts of energy. These bursts are so strong that they could create entire universes. Imagine that. What we once thought was completely empty is actually packed with the energy and potential to form something as huge and complex as a whole new universe. While science and philosophy have given us these amazing ideas, the truth is, we may never fully understand the true nature of nothing. But one thing is clear. This mystery is far from simple. It is one of the most fascinating questions of all. The more we think about it, the more we realize that the story of how everything began, the origin of everything we know, is just as incredible and mind-blowing as the universe itself. This idea of nothingness has amazed people for centuries. Ancient philosophers, from the Greeks to early Eastern thinkers, wondered about its meaning, and now modern scientists are uncovering even more unbelievable facts. From the quiet thoughts of those ancient minds to the groundbreaking discoveries happening in laboratories today, the idea of nothing continues to fill us with wonder. And as we look up at the night sky, filled with billions of stars and galaxies, we are reminded that the most incredible story of all may be the one that begins with nothing. In the vastness of space, where we see the shining stars and the swirling beauty of galaxies, it's humbling to think that these wonders might have come from what seemed like complete emptiness. The universe, as we know it, could have started from nothing at all, and this idea, the possibility of something being created from nothing, is what makes our universe and our place in it so exciting and mysterious. As we try to understand where our universe came from, we run into one of the biggest puzzles in modern science: the singularity. This mysterious point lies at the very core of the Big Bang, and scientists believe that everything we see today, space, time, matter, and energy, came from it. But this leads to an even bigger question. What existed before the Big Bang? Imagine a place where the rules of physics stop making sense. A singularity is a point where matter is packed into an infinitely small space, becoming so dense that gravity becomes unimaginably strong. In this extreme state, space and time twist and collapse in ways we can't fully understand. Even the most advanced scientific equations, like Einstein's general theory of relativity, fail to describe what happens inside a singularity. This means that, based on our current understanding, the laws of physics simply break down. The singularity that started our universe was even more mind-boggling than the ones found in black holes. Instead of being trapped inside a collapsing star, this singularity marked the very beginning of everything. At that moment, all of existence was compressed into a tiny, unbelievably hot and dense point, a state where no known physical laws applied. Then, in a single instant, this singularity expanded with incredible force, giving birth to space, time, and all the matter that would eventually form galaxies, stars, and planets. This explosive event is what we now call the Big Bang. Asking, what happened before the Big Bang, is tricky because it assumes that time already existed. But, according to Einstein's theory of relativity, space and time are woven together into one fabric called spacetime. If the Big Bang created spacetime itself, then time as we know it didn't exist before that moment. In other words, the very idea of before might not even make sense. However, some scientists believe there might be more to the story. Several theories attempt to explain what could have come before the Big Bang. Some scientists propose that the universe didn't appear from nothing, but instead goes through endless cycles of birth, expansion, and collapse. In this model, the universe expands for billions of years, reaches a peak, then shrinks back into a singularity before exploding into another Big Bang. If this theory is true, then something has always existed. Our current universe is just the latest version in an infinite series of universes. Quantum physics, the strange science that describes tiny particles, suggests that tiny bits of matter and energy can pop in and out of existence, even in what seems to be empty space. Some scientists propose that the entire universe may have emerged from one of these random quantum fluctuations. In this view, before the Big Bang, there was a vast emptiness where tiny, unpredictable quantum events took place. Eventually, one of these fluctuations led to the birth of our universe. Another idea suggests that our universe is just one of many. According to the multiverse theory, an infinite number of universes exist, each with its own unique properties. If this is true, then our universe was not the first and will not be the last. Something has always existed. It just wasn't necessarily our universe. Before the Big Bang, there may have been another universe or an entirely different state of reality. In the 1970s, brilliant physicists Stephen Hawking and Roger Penrose made groundbreaking discoveries about singularities. By combining Einstein's general relativity with quantum mechanics, the strange rules that govern tiny particles, they gained new insights into how singularities work. Their research showed that singularities are not just theoretical concepts, but real points where physics as we know it collapses. They proved that if you rewind time to the very start of the universe, you reach a moment where space bends infinitely, and time itself ceases to function in any normal way. This means that before the Big Bang, there was no recognizable space, no ticking clock, no past, just an incomprehensible state of infinite density. Science has given us incredible insights into how the universe evolved after the Big Bang, but the moment before remains one of the greatest mysteries. If time itself began with the Big Bang, then asking what came before might not make sense at all. However, many scientists believe that we simply haven't yet discovered the right laws of physics to explain what happened. In our everyday lives, time feels like an unstoppable river, always flowing from one moment to the next. We naturally think in terms of before and after, yesterday, last year, even thousands of years ago. But when we try to apply this logic to the birth of the universe, things become far more complicated. At the center of this great mystery is the idea of the singularity, a point where all the known rules of physics stop making sense. Some scientists think that time itself began with the Big Bang, meaning there was no before at all. In this view, asking what happened before the Big Bang would be like asking what lies beyond the North Pole. There is simply no direction left to go. This suggests that time, as we experience it, only exists inside our universe and did not exist before it was born. But not all scientists agree with this idea. Some believe that the singularity may not have been the true beginning, but instead came from something that already existed. One theory suggests that the universe could have appeared from tiny, unpredictable bursts of energy in an empty void, random changes that somehow sparked the creation of everything. Another theory suggests that our universe is just one in an endless cycle, where an older universe collapsed in on itself and then gave birth to a new one. While these ideas are highly uncertain and stretch the limits of human understanding, they open the door to exciting possibilities about what might exist beyond what we can see. One of the greatest minds to explore these mysteries was the famous physicist Stephen Hawking. He dedicated much of his life to studying black holes, strange objects in space where gravity is so strong that nothing, not even light, can escape. Interestingly, the center of a black hole has a singularity, much like the one thought to exist at the beginning of the universe. By studying black holes, scientists hope to uncover secrets about the earliest moments of existence. In one of his most groundbreaking discoveries, Hawking revealed that black holes are not completely dark, as people once thought. Instead, they slowly leak energy in the form of what is now called Hawking radiation. This discovery was shocking because it meant that black holes can shrink over time and eventually disappear. It also raised an even deeper question. When a black hole fades away, what happens to all the information it once held? Does it truly vanish, or could there be some unknown way for it to survive? This mystery challenges our very understanding of the universe. The study of singularities, whether inside black holes or at the birth of the universe, reveals a major problem in modern science. The two most powerful theories we have, Einstein's general theory of relativity, which explains gravity and the movement of large objects like planets and galaxies, and quantum mechanics, which describes the tiny world of atoms and particles, do not fit together. At the extreme conditions of a singularity, these two great theories break down, leaving scientists searching for a better explanation. Many physicists believe that the missing key is something called quantum gravity, a theory that would combine relativity and quantum mechanics into one complete framework. If such a theory were found, it could help us understand what really happens inside a black hole, what took place during the Big Bang, and whether anything existed before it. For many decades, scientists have worked tirelessly to uncover this missing link. They have developed countless theories and created complex mathematical models, but so far, no one has been able to fully prove how gravity behaves on the smallest, quantum level. This mystery is crucial because it prevents us from fully understanding one of the most important events in the history of the cosmos, the singularity at the birth of the universe. The singularity is not just the starting point of our universe, it also represents a barrier to our knowledge. It marks the moment when space, time, and matter first emerged, yet it also stands as a wall that science has not yet broken through. In our everyday lives, we understand reality in simple ways. Things have causes and effects, space has 3 dimensions, and time moves forward like an arrow. But the singularity challenges all of these ideas. It forces us to think beyond what we can see, measure, or even fully imagine. What if the laws of physics we rely on only began to exist after the Big Bang? What if time itself, as we know it, was not present before that moment? These questions lead us to some of the oldest and deepest mysteries ever considered by humanity. What does it mean to exist? How did something come from nothing? Can we ever truly understand the exact moment when the universe was born? These thoughts have fascinated philosophers, scientists, and thinkers for thousands of years, and they remain at the heart of our search for knowledge. As technology improves, we continue pushing the boundaries of what we know. Advanced telescopes allow us to look deeper into space. Particle colliders help us understand the tiniest building blocks of reality, and new theories attempt to bring together the vast and the microscopic into one complete picture. Yet, the singularity remains a mystery, an unsolved puzzle that challenges us to expand our minds beyond everything we currently understand. It is both an invitation and a challenge, calling us to explore the greatest secrets of the cosmos and the true nature of reality itself. Dark matter is one of the biggest mysteries in astronomy. It's a strange and invisible kind of matter that we can't see because it doesn't give off or reflect light, nor does it interact with any kind of radiation. Despite this, scientists are certain it exists because of the unusual way it affects gravity. When we look at galaxies, we see that their movement and formation don't follow the usual rules of physics unless there is much more matter present than we can actually observe. This hidden matter influences how galaxies spin, how they cluster together, and even how light bends when passing by massive objects, a phenomenon known as gravitational lensing. Its presence can also be detected in the way the universe is structured and in the faint glow left over from the Big Bang, called the cosmic microwave background. According to the most widely accepted model of the universe, called the lambda cold dark matter model, all the mass and energy in the universe is divided into 3 main parts. Ordinary matter, which makes up everything we can see, like stars, planets, and people, accounts for only 5%. Dark matter, the unseen force holding galaxies together, makes up about 26.8%. The remaining 68.2% is dark energy, a mysterious force that is driving the universe to expand at an accelerating rate. This means that about 85% of all the mass in the universe comes from dark matter, and together, dark matter and dark energy account for an overwhelming 95% of everything that exists. Scientists still don't know exactly what dark matter is. It doesn't seem to interact with normal matter or light except through gravity, which makes it incredibly difficult to detect with our current technology. The leading theory is that dark matter could be made up of tiny, unknown particles, such as weakly interacting massive particles, WIMPs, or axions. Another idea is that dark matter could be made of ancient black holes that formed in the early universe. Researchers also classified dark matter based on how fast its particles move. If the particles move very quickly, it's called hot dark matter. If they move at moderate speeds, it's warm dark matter. But most scientists believe that dark matter is cold, meaning its particles move very slowly. This slow movement allows dark matter to clump together over time, helping to form the structures of galaxies and galaxy clusters. Although dark matter is widely accepted by most astrophysicists, there are still a few who question it. Some scientists believe that the strange effects we see in space might not be caused by an invisible form of matter, but instead by a flaw in our understanding of gravity. They have proposed alternative theories, such as modified Newtonian dynamics, which suggest that gravity behaves differently on very large scales. However, none of these alternative ideas fully explain all the evidence. While it's possible that our understanding of gravity needs some adjustments, dark matter still seems to be a crucial part of the cosmic puzzle. The idea of dark matter has been around for more than a century, and the story of its discovery is filled with brilliant scientists, surprising observations, and groundbreaking theories. It all started in the late 19th century when researchers began noticing strange patterns in the way stars and galaxies moved. In the year 1884, a Scottish scientist named William Thomson, who is better known as Lord Kelvin, made an interesting discovery. He was studying the number of stars around our Sun and trying to estimate how densely packed they were. He analyzed how these stars moved and calculated that if there were about 1 billion stars within a certain distance of the Sun, 1 kiloparsec, which is about 3,260 light-years, then their movements would not make sense unless there was more unseen matter influencing them. Although Kelvin didn't call it dark matter, his observations laid the foundation for future research. Around the same time, he also estimated the age of the Sun to be between 20 and 100 million years, but this turned out to be incorrect. Still, his curiosity about the hidden forces in space helped open the door to new ideas. Then, in the year 1906, a French mathematician and physicist named Henri Poincaré took the discussion a step further. He introduced the term dark matter, or matière obscure, while reviewing Lord Kelvin's work. Poincaré suggested that there might be unseen mass spread throughout the universe, though he believed that this hidden mass was less significant than the visible matter we can observe. His estimates weren't accurate, but by giving dark matter a name, he helped bring the idea into mainstream scientific discussions. In the early 20th century, more astronomers became intrigued by the idea of invisible matter shaping the cosmos. In the year 1922, a Dutch astronomer named Jacobus Kapteyn studied how stars moved and noticed that their motion didn't always match what would be expected based on visible matter alone. This was one of the earliest signs that dark matter might exist. A few years later, in the year 1930, a Swedish scientist named Knut Lundmark added more evidence to the case. He observed that galaxies appeared to have far more mass than what could be accounted for by the stars, gas, and dust visible in telescopes. His work was groundbreaking because it suggested that the universe contained vast amounts of hidden mass. Then, in the year 1932, another Dutch astronomer, Jan Oort, made an important contribution. He was studying how stars moved within our galaxy, the Milky Way, and found that the mass of the galaxy seemed much larger than what could be seen. He concluded that there must be some kind of invisible material adding extra weight to the galaxy. However, later research showed that Oort's measurements were not entirely accurate, and more work was needed to fully understand the nature of this unseen mass. In the year 1933, a Swiss astrophysicist named Fritz Zwicky made a groundbreaking discovery while studying clusters of galaxies at the California Institute of Technology. While examining a massive collection of galaxies known as the Coma Cluster, he noticed something very unusual. The galaxies were moving much faster than they should have been based on the amount of visible matter present. This led him to propose the idea that there must be a vast amount of invisible mass, which he called dunkle materie, or dark matter. Zwicky estimated that the total mass of the Coma Cluster was about 400 times greater than what could actually be seen through telescopes. He believed that this hidden mass was creating a strong gravitational pull, keeping the galaxies from flying apart. Although his calculations were not entirely accurate, mainly because of outdated values, he was one of the first scientists to recognize that the universe contained an unseen force that influenced the movement of galaxies. However, Zwicky had a different interpretation of dark matter than what scientists believe today. He thought it was made of ordinary matter that simply did not emit light, rather than an entirely new and mysterious form of matter. Despite this, his work was a crucial first step in uncovering one of the greatest cosmic mysteries. As time went on, more scientists found evidence that supported the idea of dark matter. In the year 1939, an astronomer named H.W. Babcock studied the movement of stars in the Andromeda Galaxy, the closest spiral galaxy to our own. He discovered that stars near the outer edges of the galaxy were moving much faster than expected. This suggested that Andromeda contained a lot more mass than what was visible. Initially, Babcock thought that this strange motion might be caused by light being absorbed within the galaxy, or that the structure of the galaxy itself changed in its outer regions. But in reality, his findings hinted at the presence of a massive, invisible force affecting the galaxy's rotation. Then, in the following year, 1940, another astronomer, Jan Oort, made a similarly important discovery. While studying a galaxy called NGC 3115, he found evidence of a vast, unseen halo of mass surrounding it. This was yet another clue that galaxies contained much more matter than could be detected with available technology. The real shift in thinking happened during the 1970s, when astronomers gathered enough evidence to suggest that entire galaxies were enveloped by enormous, invisible halos of matter. In the year 1974, two separate groups of scientists reached the same conclusion. One team, based in Princeton, New Jersey, included Jeremiah Ostraker, Jim Peebles, and Amos Yahiel, while the other, from Tartu, Estonia, was led by Jan Einasto, N. Saar, and Ants Karsik. Their independent research strengthened the idea that galaxies were surrounded by vast amounts of hidden mass. One of the most compelling pieces of evidence for these mysterious halos came from studying how galaxies rotate. Astronomers used both optical and radio telescopes to analyze the movement of stars and gas within galaxies. Vera Rubin and Kent Ford, using a new type of instrument called a spectrograph, made precise measurements of how fast stars moved at different distances from the center of spiral galaxies. What they found was astonishing. The stars at the edges were moving just as fast as those closer to the center, which defied expectations based on the visible mass alone. At the same time, radio astronomers were making their own discoveries. By studying the 21-centimeter wavelength emitted by atomic hydrogen, they were able to observe the movement of gas in galaxies far beyond the regions where visible stars could be detected. This allowed them to measure rotation speeds at much greater distances. Early observations of the Andromeda Galaxy, using enormous telescopes such as the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, revealed something surprising. The hydrogen gas at the galaxy's edges was not slowing down as expected. According to Kepler's laws, which describe how planets and stars should orbit a central mass, the speed should have decreased with distance, but it remained nearly constant instead. As telescope technology advanced, astronomers were able to push their measurements even further. In the year 1975, researchers Roberts and Whitehurst extended their analysis of Andromeda's rotation curve all the way out to a distance of 30 kiloparsecs, an enormous span of space. Their results showed that even at such great distances, the galaxy's rotation speed remained steady. This meant there had to be a vast amount of unseen matter surrounding the galaxy, providing additional gravitational force. Their research combined optical data from stars with radio data from hydrogen gas, painting a clear picture. The outer regions of galaxies contained far more mass than what was visible. Around the same time, astronomers were using even more sophisticated tools to examine galactic motion. In the year 1972, scientists Rogstad and Shostak used an advanced technique called interferometry, where multiple radio telescopes work together as one, to study the hydrogen rotation curves of 5 different spiral galaxies. They found that all 5 had the same unexpected pattern. Their outer regions were rotating at nearly the same speed as their inner regions. This was yet another sign that an enormous amount of hidden mass was influencing galactic movements. By the late 1970s, the existence of dark matter was no longer just a theory. It was widely accepted as one of the biggest unsolved mysteries in astronomy. Scientists realized that this invisible substance was not just present in individual galaxies, but likely spread throughout the entire universe. In the years between 1980 and 1999, scientists started collecting more and more evidence that pointed to the existence of dark matter. One of the most important studies came in the year 1996, when researchers Persic, Salucci, and Stell closely examined 967 spiral galaxies. What they found was astonishing, strong proof that something invisible yet incredibly massive was influencing the movement of these galaxies. Other key pieces of evidence also began to pile up. Scientists noticed a strange effect called gravitational lensing, where massive galaxy clusters acted like cosmic magnifying glasses, bending light from objects behind them. They also observed the way hot gas was spread out in galaxies and clusters and saw unusual temperature patterns in the cosmic microwave background, the faint glow left over from the Big Bang. All of these clues pointed to the same mystery. A hidden form of matter must be shaping the universe. Today, nearly all experts agree that dark matter is made of unknown particles, particles that are unlike anything we have ever discovered. Finding these mysterious particles has become one of the biggest challenges in modern physics. Scientists all over the world are conducting experiments and using powerful machines to try to uncover the truth about what dark matter really is. To understand dark matter better, we first need to know how different forms of energy behave in the universe. Matter, which includes things like galaxies, stars, and planets, spreads out as the universe expands. Its density decreases in a predictable way, shrinking as the cube of the universe's expansion. That means as space gets bigger, the matter in it becomes thinner. Radiation, such as light and cosmic rays, fades away even faster. It follows the inverse fourth power of expansion, meaning its energy weakens much more rapidly as space stretches. But there is something unusual called the cosmological constant, which behaves differently. Unlike matter and radiation, its energy density does not change at all, no matter how large the universe grows. This strange difference comes from a phenomenon called radiation redshift. Imagine the universe expanding like a balloon being blown up. If the universe doubles in size, the scale factor of its expansion doubles too. As this happens, the energy of things like the cosmic microwave background, the faint radiation left over from the Big Bang, gradually weakens. This happens because light waves get stretched as space grows, reducing their energy. The same effect applies to tiny, fast-moving particles like early neutrinos, which also lose energy as the universe expands. However, the cosmological constant is different. It is a property of space itself, and its energy remains unchanged no matter how much space grows. Dark matter, as a concept, refers to the invisible mass that exists in the universe but does not emit light. However, scientists use the term in a more specific way to describe an unknown type of matter that isn't made of the usual particles we know about. It is different from missing baryons, which are ordinary particles like protons and neutrons that are simply hard to detect. Because dark matter is invisible, scientists have had to rely on indirect clues to study it. One of the strongest hints of dark matter comes from the way spiral galaxies rotate. In a typical system, like our solar system, most of the mass is concentrated in the center, which means objects farther out move more slowly. This follows Kepler's third law, which explains why planets like Mercury, which are close to the Sun, orbit much faster than distant planets like Neptune. But when scientists looked at galaxies, they saw something surprising. Stars at the edges of galaxies were moving just as fast as those near the center. This should be impossible if all the galaxy's mass was visible. The only explanation is that there is a huge amount of unseen mass spread throughout the galaxy, providing extra gravitational pull. This hidden mass is what we call dark matter. The way mass is distributed in galaxies also follows something called the virial theorem. a rule that helps astronomers estimate the total mass of a system based on how fast its stars move. But when scientists applied this rule to elliptical galaxies and dense star clusters, they noticed something odd. The speeds of the stars didn't match the amount of visible mass in these systems. Even when they took into account the complex orbits of the stars, there was still missing mass. Once again, the simplest explanation was that there must be more mass than what we can see. Yet another sign that dark matter is out there. Galaxy clusters provide another powerful way to measure dark matter, and scientists have three main ways to do this. First, they look at how fast galaxies within a cluster are moving. If the cluster contained only visible matter, the galaxies wouldn't move as fast as they do. Their high speeds suggest there is extra, invisible mass keeping them bound together. Second, scientists study the X-rays given off by the hot gas inside galaxy clusters. By measuring the temperature and density of this gas, they can calculate its pressure. Since gravity and pressure must balance, this allows them to estimate the total mass of the cluster. The results show that there is far more mass present than what we can see. Third, they use gravitational lensing, when massive galaxy clusters bend light from more distant objects. By studying how this bending occurs, scientists can calculate the cluster's total mass, even without directly observing the motion of its galaxies. All three of these methods point to the same conclusion. Dark matter is real, and it outweighs normal matter by about 5 to 1. Though we cannot see it, this invisible substance plays a critical role in shaping galaxies, galaxy clusters, and the entire structure of the universe. One of the most fascinating ideas from Einstein's theory of general relativity is something called gravitational lensing. This happens when a very heavy object, like a galaxy or a group of galaxies, sits between a distant light source and someone looking at it from Earth. The massive object acts like a giant cosmic magnifying glass, bending and distorting the light as it travels through space. Because of this, the light from faraway objects can look stretched, duplicated, or warped into strange shapes. What's really important to know is that gravitational lensing works simply because mass exists. It doesn't matter what the mass is made of. The heavier an object is, the stronger its gravity will be, and the more it will bend light. Imagine a bright object, like a distant quasar, sitting behind a large cluster of galaxies. The gravity of the galaxy cluster bends the quasar's light, changing the way it appears to us. There are two main ways this bending of light can happen. When the distortion is dramatic, like when the light from background galaxies gets stretched into bright arc-like shapes, we call it strong lensing. Scientists have observed this effect in many distant galaxy clusters, including one known as Abell 1689. By analyzing the shapes of these arcs, scientists can estimate the total weight of the galaxy cluster doing the bending. The other type, called weak lensing, is much subtler. Here, galaxies don't turn into arcs, but their shapes get slightly stretched or skewed. Even though the effect is small, it's still extremely useful. By carefully measuring these tiny distortions, scientists can figure out how dark matter is spread across the universe. So far, these observations have lined up well with what scientists expect based on theories of dark matter. Both ordinary matter, the stuff we can see and touch, and dark matter are types of matter, but they behave very differently. In the early universe, ordinary matter carried an electric charge, which meant it reacted with light and was constantly bouncing around. This made it difficult for ordinary matter to clump together. Dark matter, however, doesn't interact with light at all, which allows it to influence the universe in other ways. One of the most important ways dark matter makes its presence known is by affecting something called the cosmic microwave background, CMB. This is the faint glow of leftover radiation from the Big Bang. Dark matter's gravity shapes how ordinary matter moves and clumps together, leaving behind clear patterns in this ancient radiation. The CMB is almost perfectly smooth in temperature, but scientists have found tiny variations, only about 1 part in 100,000, that reveal important clues about the early universe. These tiny fluctuations, called anisotropies, can be mapped across the sky. When scientists turn this map into a graph, called the angular power spectrum, they see a series of peaks at different heights. These peaks hold key information about the composition and structure of the universe. Scientists first discovered these tiny variations in 1992 using a satellite called COBE. However, COBE's measurements weren't detailed enough to see the exact shape of the peaks. In the year 2000, a high-altitude balloon experiment named Boomerang measured the first of these peaks. Later, spacecraft like WMAP and Planck provided even more precise data, confirming that the universe's structure fits the lambda-CDM model, the leading theory in modern cosmology. After the Big Bang, the universe started out as a nearly uniform sea of particles. There were no galaxies, no stars, just an almost perfectly even spread of energy and matter. However, tiny differences in density existed, and over time, these small irregularities grew larger, pulling in more matter due to gravity. This process, known as structure formation, is what led to the creation of galaxies, galaxy clusters, and even vast cosmic superstructures. In the very early universe, radiation was much more powerful than matter, and its intense energy kept ordinary matter from clumping together. If the universe had contained only ordinary matter, there wouldn't have been enough time for galaxies to form. The key to solving this problem is dark matter. Because it doesn't interact with radiation the way ordinary matter does, dark matter was able to form dense regions first. These dense pockets of dark matter created strong gravitational wells that later helped ordinary matter fall in and form galaxies. Essentially, dark matter acted as a scaffolding for the cosmic structures we see today. One of the most striking pieces of evidence for dark matter comes from an object called the Bullet Cluster, which was formed by the collision of two enormous galaxy clusters. What makes it so fascinating is that when scientists mapped the mass in this system using gravitational lensing, they found that the bulk of the mass wasn't located where the visible matter was. This is a huge problem for alternative theories of gravity, which predict that lensing should only happen around visible matter. However, the standard dark matter theory explains it perfectly. When the two galaxy clusters collided, their ordinary matter, mostly hot gas, interacted through electromagnetic forces, slowing down and staying in the middle. Dark matter, however, doesn't interact with light or electromagnetic forces. Because of this, it kept moving through the collision nearly undisturbed, separating from the visible gas. When astronomers used gravitational lensing to map the true mass distribution, they found two separate mass peaks, one from visible matter and one from dark matter. This was a major confirmation that dark matter is a real and separate component of the universe. In addition to dark matter, scientists study another mysterious force in the universe: dark energy. One of the best ways to measure the universe's expansion is by using Type Ia supernovae, exploding stars that always shine with the same brightness. Because we know how bright they should be, we can compare this to how dim they appear to estimate their distance from Earth. Observations of these supernovae have led to a surprising discovery. The universe isn't just expanding, it's expanding faster and faster. This strange, accelerating expansion is believed to be caused by dark energy, a mysterious force that makes up about 70% of the universe. One of the most fascinating is something called baryon acoustic oscillations, or BAO for short. Imagine the universe as a hot, dense sea of energy and particles in its earliest days, more than 13 billion years ago. Back then, sound waves rippled through this cosmic soup, creating waves in the density of matter. These waves left a lasting imprint on the universe, shaping the way galaxies are distributed even today. Before atoms could form, the universe was filled with a thick, glowing plasma made of light, photons, and regular matter, baryons. In this hot environment, sound waves traveled through the plasma, pushing matter into rippling patterns. Once the universe cooled down enough for atoms to form, these waves froze in place. The result? Even now, when scientists look at the arrangement of galaxies, they see a faint but measurable pattern. Galaxies are slightly more likely to be separated by about 147 million light-years. This cosmic pattern was first predicted in the 1990s, and in the year 2005, massive galaxy mapping projects like the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey confirmed it. By studying these ancient ripples alongside observations of the cosmic microwave background, the afterglow of the Big Bang, scientists can fine-tune their understanding of the universe's expansion and the amount of matter it contains. All of these findings support the leading model of the universe, known as the Lambda CDM model. To map out the large-scale structure of the universe, astronomers use galaxy redshift surveys. Redshift is a key measurement that tells us how fast an object is moving away from us due to the expansion of the universe. But redshift isn't always straightforward. It has two parts. The main component comes from the overall expansion of space, but a smaller portion is due to a galaxy's own movement, known as its peculiar velocity. This brings us to an interesting cosmic tug-of-war. Clusters of galaxies, called superclusters, pull matter toward them with their gravity, which slows down their expansion compared to the rest of the universe. Meanwhile, vast empty spaces called voids expand even faster than average. Because of this, galaxies near superclusters don't behave exactly as we'd expect. If a galaxy is in front of a supercluster, it is falling toward it faster than normal, making its redshift slightly higher than expected. If a galaxy is behind the supercluster, it appears to be moving more slowly than expected, lowering its redshift. This odd effect makes superclusters look squashed when viewed through redshift data, while voids appear stretched. However, because we don't know the exact shape of individual superclusters, it's hard to notice this effect by looking at just one. Instead, scientists observe many superclusters and voids and average their data to reveal this pattern. This phenomenon was first predicted by physicist Nick Kaiser in the year 1987, and in the year 2001, it was confirmed by the 2-degree Field Galaxy Redshift Survey. The results matched perfectly with predictions from the Lambda CDM model, reinforcing our understanding of how cosmic structures evolve. Another related discovery comes from something called the Lyman alpha forest. This is a series of absorption lines found in the light from distant galaxies and quasars. These lines appear because neutral hydrogen in space absorbs light at a specific wavelength known as the Lyman alpha transition. By studying this effect, scientists can refine their models of the universe, and their findings align closely with data from missions like the Wilkinson Microwave Anisotropy Probe, WMAP. Dark matter, one of the most mysterious substances in the universe, is usually classified into three types: cold, warm, and hot. These names don't refer to temperature, but to how fast the particles were moving in the early universe. The key idea is something called the free streaming length, which is the distance a particle could travel before the universe expanded and slowed it down. The classification of dark matter depends on how this free streaming length compares to the size of a protogalaxy, one of the earliest cosmic structures that would later grow into a full galaxy. If the free streaming length is much smaller than a protogalaxy, the dark matter is considered cold. If it is roughly the same size as a protogalaxy, it is called warm, and if it is much larger, it is hot. In the 1990s, some scientists believed that a mix of these types could explain the universe's structure, but after the discovery of dark energy, those ideas became less popular. To understand why free streaming length matters, imagine the early universe as a place where tiny quantum ripples created small differences in density. Over time, particles moved from dense regions to less dense ones, but their motion was limited by the rapid expansion of space. Faster particles, like those in hot dark matter, traveled farther before they were slowed down, while slower ones, like cold dark matter, didn't get very far. This difference in movement had a huge impact on the way cosmic structures formed. If hot dark matter dominated, then the largest structures, superclusters, would have formed first, later breaking apart into galaxies. If cold dark matter was dominant, galaxies would form first, grouping together later into clusters and superclusters. Observations of deep space images confirm that galaxies formed first, meaning cold dark matter is the main type that shaped the universe. Neutrinos, which travel almost at the speed of light, are an example of hot dark matter. However, because galaxies formed early, neutrinos alone cannot explain the universe's structure. This is one of the reasons scientists believe dark matter is mostly cold, which fits well with all the latest observations and theories. Dark matter is a mysterious form of matter that doesn't give off light and is almost impossible to see directly. However, it does interact with the universe in one major way, through gravity. This means that dark matter might not be something entirely new. It could, in theory, include ordinary matter like the tiny building blocks of atoms, protons and neutrons. Many space objects that astronomers study, such as planets, failed stars known as brown dwarfs, small dim stars called red dwarfs, burnt-out stars like white dwarfs, super-dense neutron stars, and even black holes, all fit into this category. A black hole, for example, doesn't care what kind of matter falls into it. Whether it's a regular atom or an unknown type of dark matter, once it crosses the point of no return, the event horizon, it gets treated the same way. Scientists once believed that dark matter might mostly be made up of these hard-to-spot objects, which are known as MACOs, short for massive compact halo objects. However, as research progressed, this idea was largely ruled out. There are several reasons why scientists now believe that dark matter is mostly not made of regular matter. First, if dark matter were just hidden clouds of gas or dust, we would expect to see them glow faintly when they reflect or absorb light from stars. But no such vast amounts of glowing matter have been found. Second, scientists use the Big Bang theory to understand how the elements in the universe were formed. If there had been more ordinary matter, called baryonic matter, in the early universe, we would expect to see larger amounts of certain elements, like helium and lithium, than we actually do. Observations suggest that normal matter makes up only about 4 to 5% of everything in the universe. However, based on the way galaxies behave, scientists know that the total amount of matter needed to explain the universe's structure should be closer to 30%. This means there must be a lot of invisible matter we can't see directly. Further research has shown that only a small fraction of dark matter could be hidden objects like tiny planets or black holes. One method scientists use to detect dark matter is gravitational microlensing, which measures how objects bend light as it passes by. The results suggest that these known objects cannot account for most of the missing mass. Another key piece of evidence comes from studying the cosmic microwave background, the faint radiation left over from the Big Bang. Data from missions like WMAP and Planck reveal that about 5/6 of all matter in the universe is something that doesn't interact much with light or normal matter, except through gravity. This strongly suggests that most of dark matter is completely invisible and can only be detected through its gravitational pull. If ordinary matter isn't responsible for most of the universe's hidden mass, then dark matter must be something else, specifically non-baryonic matter. Scientists have narrowed it down to two main possibilities: strange, new particles that we haven't directly observed yet, ancient black holes that formed in the early universe, long before the first stars. Unlike normal matter, these mysterious particles wouldn't have played a role in creating the elements during the Big Bang, a process called nucleosynthesis. Instead, we only notice them because of their gravitational effects, such as how they bend light, a phenomenon known as weak lensing. Some types of dark matter may even interact with themselves or with ordinary matter. For example, WIMPs, weakly interacting massive particles, are a leading dark matter candidate. If WIMPs exist, they might occasionally collide with each other and produce detectable signals, such as bursts of gamma rays or streams of invisible particles called neutrinos. Scientists are searching for these signs using sophisticated detectors. WIMPs are thought to be fundamental particles similar to those we already know, but interacting mainly through gravity and perhaps the weak nuclear force. Many theories suggest that these particles were created in the early universe in a way similar to normal particles. If they exist, WIMPs would form what is known as cold dark matter. To explain the amount of dark matter in the universe today, WIMPs would need to be able to destroy each other in a specific way, which matches predictions if they have masses around 100 billion electron volts and interact via the electroweak force. This idea is often called the WIMP miracle because it fits surprisingly well with theories that extend the standard model of particle physics. A long-standing theory called supersymmetry predicts the existence of stable partner particles, one of which could be dark matter. Scientists are trying to detect WIMPs by searching for the signals their interactions might produce, such as gamma rays or neutrinos coming from space. They are also using underground experiments to catch WIMPs colliding with atomic nuclei and attempting to create them in high-energy particle colliders like the Large Hadron Collider, LHC. However, in the early 2010s, experiments at the LHC failed to find strong evidence for supersymmetry, casting doubt on the simplest WIMP models. Since WIMPs have not been detected, another candidate for dark matter has gained attention: axions. These are tiny, almost massless particles first proposed in the year 1978 by physicists Frank Wilczek and Steven Weinberg. Axions were originally suggested to solve a problem in quantum chromodynamics, QCD, the theory that explains how quarks and gluons interact. Unlike WIMPs, axions are incredibly light and barely interact with anything, making them hard to detect. However, they could have been produced in the early universe and might still exist in large amounts today. Axions have been suggested as a way to solve some of the small-scale mysteries of the leading cosmological model, known as the Lambda CDM model. As the search for WIMPs has not yet succeeded, interest in axions has grown. Because these particles are so light, their strange quantum properties might help explain certain unexplained cosmic patterns. Another idea is that dark matter could consist of primordial black holes, ancient black holes formed in the very early universe shortly after the Big Bang. Instead of forming from dying stars like regular black holes, these black holes could have formed when tiny but extremely dense regions of space collapsed under their own gravity. This would mean that black holes existed even before the first stars were born. If primordial black holes exist, they could range in size from microscopic, as small as an atom, to enormous, even larger than the black holes formed from collapsed stars. The idea of primordial black holes, tiny black holes that may have formed in the early universe, was first proposed in the year 1967 by two physicists, Yakov Zeldovich and Igor Novikov. A few years later, in 1971, the famous scientist Stephen Hawking expanded on the concept. The theory quickly gained attention because it offered a possible explanation for one of the biggest cosmic mysteries: dark matter. Unlike other exotic dark matter theories, primordial black holes were appealing because black holes are already a well-established part of physics, specifically in Einstein's theory of general relativity. Scientists already knew that black holes existed, so if some of them had formed in the very early universe, they could potentially account for dark matter. However, forming primordial black holes would require special conditions, such as rapid cosmic expansion, beyond what the standard model of physics predicts. In the year 2015, a major discovery reignited interest in primordial black holes. Scientists detected gravitational waves, ripples in space-time, caused by black holes merging. Some of the black holes involved in these collisions were unexpectedly massive, larger than what would normally form from collapsing stars. This raised the possibility that they might be primordial black holes rather than the usual stellar ones. However, when researchers searched for signs of gravitational lensing, a bending of light caused by the gravity of unseen objects, they found no evidence that medium-sized black holes, potential dark matter candidates, were scattered throughout space. Still, some experts believe that the lack of detection might be due to incorrect assumptions about the mass of these black holes. With new technology like the James Webb Space Telescope, scientists hope to get a clearer picture. For a time, scientists thought that tiny primordial black holes could make up a significant portion of dark matter. However, when the Voyager 1 spacecraft traveled beyond the influence of the Sun, it measured streams of positrons and electrons in deep space. The results were unexpected. The number of these particles was too low, and their energy levels did not match what would be expected if small primordial black holes were abundant. Because of this, scientists concluded that these miniature black holes were likely too rare to explain dark matter. Even though primordial black holes may not be the answer, researchers are still investigating other dense forms of dark matter. Some theories even explore whether dark matter could be cooled down in ways that allow it to form compact objects. But as of the year 2018, the mystery remains unsolved. In 2019, astronomers studying the Andromeda Galaxy found no evidence of microlensing, which would have been a sign of tiny black holes bending light from distant stars. This further weakened the case for primordial black holes as dark matter. Yet, there is still an unexplored gap in our understanding. There exists a mass range that is too small to be detected with current microlensing techniques, and it is possible that primordial black holes of this size could still account for all dark matter. This remains an open question in astrophysics. If dark matter is made up of mysterious particles that barely interact with anything, scientists face another important question. Could these particles clump together to form objects like planets, stars, or even black holes? Historically, the answer has been no, and there are two main reasons for this. Dark matter cannot easily lose energy. Normal matter can form stars and planets because it has many ways to lose energy. When gas clouds in space collapse under gravity, they release energy as heat and light, allowing them to condense into dense structures like stars. However, dark matter doesn't seem to have this ability. Since it barely interacts with anything except through gravity, it cannot easily cool down and slow down. Instead of forming compact objects, dark matter particles that start falling inward would just gain speed and escape. Dark matter does not interact in multiple ways. Regular matter is able to form complex structures because it interacts through several forces, including gravity, electromagnetism, and nuclear forces. These interactions allow atoms to form, stars to burn, and galaxies to take shape. Inside stars, nuclear fusion produces light and heat, but dark matter doesn't seem to have any significant interactions beyond gravity. This means it cannot form atoms, emit radiation, or create structures like stars and planets. If dark matter consists of tiny, weakly interacting particles, they would constantly be passing through every square centimeter of Earth millions or even billions of times per second. Scientists have been trying to detect them using different experiments. One of the most studied dark matter candidates is called WIMPs, weakly interacting massive particles. But another possibility is axions, which are gaining interest through projects like the Axion Dark Matter Experiment, ADMX. Other theories suggest that dark matter could be made of heavy particles from a hidden sector of physics that only interact with regular matter through gravity. There are two main types of experiments designed to detect dark matter: direct detection experiments. These attempt to observe dark matter particles as they collide with atoms. Scientists use ultra-sensitive detectors to look for tiny bursts of energy when a dark matter particle interacts with a nucleus. Because these signals are incredibly faint, these experiments are conducted deep underground, where they are shielded from cosmic radiation. Some famous underground laboratories include the Starwell Mine in Australia, the Sudan Mine in the United States, and the Gran Sasso National Laboratory in Italy. There are two common technologies used in these experiments: cryogenic detectors. These measure tiny temperature changes when dark matter particles hit materials like germanium. Noble liquid detectors. These use substances like xenon or argon, which give off flashes of light when struck by particles. Some of the most advanced experiments in these areas include CDMS, CRESST, Xenon, and LUX. Indirect detection experiments. These look for signs of dark matter by searching for its effects in space. If dark matter particles can annihilate or decay, they might release gamma rays, positrons, or neutrinos that can be detected by telescopes. One intriguing claim comes from the Dharma or Libra experiment, which has recorded a mysterious yearly fluctuation in its data. Some believe this could be caused by Earth moving through a dark matter cloud. However, other experiments like LUX and Super CDMS have not observed the same effect, making it an unsolved puzzle. Scientists also use directional detection experiments to track the motion of dark matter based on the movement of the solar system through the Milky Way. Instruments like DMTPC and DRIFT aim to detect the direction of incoming dark matter particles, helping to separate real signals from background noise. Another way to search for dark matter is to look for it using high-energy telescopes. If dark matter particles collide, they might release bursts of gamma rays. The Fermi Gamma Ray Space Telescope, launched in 2008, has detected unusual gamma ray signals from the center of the Milky Way. Some researchers believe these could be hints of dark matter annihilation, while others think they might come from pulsars. Other experiments, such as the Alpha Magnetic Spectrometer on the International Space Station, have detected unexpected amounts of positrons in cosmic rays. Some believe this could be a sign of dark matter, but it is not yet confirmed. The search for dark matter has even reached particle accelerators, like the Large Hadron Collider, LHC. If dark matter particles can be created in high-energy collisions, they might escape detection, leaving behind a gap in energy measurements. Scientists are looking for these missing energy signals to confirm the presence of dark matter. Because dark matter remains unidentified, some scientists have proposed alternative explanations. Some theories suggest that gravity itself behaves differently on cosmic scales, eliminating the need for dark matter. Ideas like MOND, modified Newtonian dynamics, and entropic gravity challenge the standard dark matter model, but they struggle to explain all the evidence. The universe is full of mysteries, and one of the biggest is dark energy. This strange force is responsible for making the universe expand faster and faster. Scientists believe that dark energy makes up about 68% of everything in the universe. In contrast, dark matter, another mysterious substance, accounts for about 26%, while all the regular matter, the stars, planets, and everything we can see, only adds up to about 5%. Other forms of energy, such as light particles, photons, and neutrinos, are so tiny in comparison that they barely count. Even though dark energy has an extremely low density, about 7 times 10 to the power of negative 30 grams per cubic centimeter, it still dominates the universe. This is because, unlike matter, which clumps together into galaxies and stars, dark energy is spread evenly across space. No matter where you go in the universe, dark energy is always there, filling every inch of the cosmos. Scientists first suspected dark energy existed when they studied distant exploding stars known as Type Ia supernovae. These supernovae act as cosmic measuring sticks because they shine with the same brightness no matter where they are. By looking at how their light stretches as it travels through space, a phenomenon called redshift, scientists can figure out how fast they are moving away. What they found was shocking. Instead of slowing down, the universe was expanding faster and faster. This was the opposite of what scientists expected. Before this discovery, most believed that gravity from all the matter in the universe would gradually slow down the expansion, much like how a thrown ball slows before falling back to the ground. But the data showed that some unknown force, was pushing the universe apart. That force was later named dark energy. There are several ideas about what dark energy could be. One of the leading explanations is called the cosmological constant. This idea suggests that dark energy is a constant, unchanging force that fills space. It's sometimes described as the energy of empty space or vacuum energy. Another possibility is that dark energy comes from scalar fields, a type of energy that changes over time and space. These fields could behave differently in different parts of the universe, making dark energy more dynamic. Some versions of this idea include quintessence and moduli fields. Other theories suggest that dark energy could interact with gravity in unknown ways. One idea, called cosmological coupling, proposes that dark energy and gravity might be linked in a way we don't yet understand. Another theory, interacting dark energy, suggests that dark energy might be influenced by other unseen forces in the universe. The idea of a mysterious energy filling space actually goes back to Albert Einstein. In the early 20th century, Einstein introduced a term called the cosmological constant, L, lambda, in his equations of general relativity. At the time, scientists believed the universe was static, neither expanding nor contracting. To make his equations fit this idea, Einstein added the cosmological constant, which acted as a force counteracting gravity, preventing the universe from collapsing in on itself. However, in 1929, the astronomer Edwin Hubble discovered that the universe wasn't static at all, it was actually expanding. This made Einstein realize that his original assumption was wrong. He later called the cosmological constant his greatest blunder. Ironically, decades later, scientists would find that a repulsive force, what we now call dark energy, was indeed pushing the universe apart, meaning Einstein's idea may not have been a mistake after all. In 1980, physicists Alan Guth and Alexei Starobinsky proposed a groundbreaking idea called cosmic inflation. This theory suggests that, just after the Big Bang, the universe went through a brief but extremely rapid expansion, growing at an unimaginable speed. This inflationary period shaped the structure of the universe and explains why galaxies are distributed the way they are today. Inflation seems similar to dark energy, as both involve the rapid expansion of space. However, the energy driving inflation was much stronger than the dark energy we observe today. Scientists are still trying to understand if these two forces are connected or if they are completely separate phenomena. By the 1980s, scientists had developed models of the universe that relied heavily on cold dark matter, CDM, a form of dark matter that moves slowly compared to the speed of light. These models did a good job explaining how galaxies formed, but they had some inconsistencies. For example, they predicted a slower Hubble constant, the rate of expansion of the universe, than what astronomers actually observed. The situation changed in 1992 when NASA's COBE spacecraft discovered slight irregularities in the cosmic microwave background, CMB, the faint glow left over from the Big Bang. This discovery pushed scientists to reconsider their models. A major breakthrough came in 1998 when astronomers studying distant supernovae found clear evidence that the universe's expansion was accelerating, not slowing down. This was the first direct proof that dark energy was real. More discoveries followed. In the early 2000s, experiments like Boomerang and Maxima analyzed the cosmic microwave background and found that the universe's total energy density was very close to what is known as the critical density, the exact amount needed to make the universe flat on large scales. However, when scientists measured the amount of matter in the universe, they found it was only about 30% of this critical density. The missing energy was explained by the presence of dark energy. Further confirmation came from the 2-degree field, 2DF Galaxy Redshift Survey in 2001, which measured the distribution of galaxies and showed that dark energy was needed to explain the observations. Then, from 2003 to 2010, NASA's WMAP satellite provided even more precise measurements of the cosmic microwave background, solidifying the lambda CDM model as the best explanation for the structure and evolution of the universe. The name dark energy was first used in 1998 by physicist Michael S. Turner, following the earlier term dark matter, which had been coined by Fritz Zwicky in the 1930s. Despite all these discoveries, dark energy remains one of the biggest puzzles in modern physics. Some scientists believe it could be a fundamental property of space itself. Others think it might be linked to quantum mechanics, the strange rules that govern particles at the smallest scales. Future experiments, including new space telescopes and large-scale galaxy surveys, aim to uncover more clues about this mysterious force. To truly grasp how the universe grows and stretches over time, scientists need to take incredibly precise measurements of its expansion. In the realm of general relativity, researchers figure out how fast the universe is expanding by studying its shape and a crucial concept known as the cosmological equation of state. This equation explains how factors like temperature, pressure, and the combined densities of matter, energy, and vacuum energy interact in different parts of space. One of the biggest challenges in modern cosmology is figuring out the equation of state for dark energy. Scientists believe dark energy plays a major role in the universe's rapid expansion, but understanding its true nature remains a mystery. To study this, researchers include a concept called the cosmological constant in the Standard Model of Cosmology, also known as the Friedmann-Lemaitre-Robertson-Walker metric. This leads to what experts call the lambda cold dark matter model, or lambda CDM model. It's often referred to as the gold standard of cosmology because it closely matches what we observe in the real universe. Since the year 2013, the lambda CDM model has been repeatedly tested and confirmed through highly accurate observations, including data from the Planck spacecraft and the Supernova Legacy Survey. Early results from this survey suggested that dark energy behaves almost exactly as Einstein's cosmological constant predicts, with an accuracy of about 10%. More recent discoveries from the Hubble Space Telescope's Higher Z team indicate that dark energy has been influencing the universe for at least 9 billion years, long before the universe began its rapid acceleration. However, despite these findings, dark energy remains one of the greatest puzzles in physics. It appears to be extremely smooth and evenly spread across space, with an incredibly low density. Unlike other forms of energy or matter, it doesn't seem to interact with anything except gravity. Its density is astonishingly small, about 1 divided by 10, followed by 27 zeros kilograms per cubic meter, making it nearly impossible to detect in laboratory experiments. Yet, despite being so faint, dark energy makes up around 68% of the universe's total energy. This is because, unlike matter, which clumps together, dark energy spreads out evenly across all of space, exerting a profound influence on the universe's expansion. One of the leading explanations for dark energy links it to something called vacuum energy. This refers to the tiny fluctuations of particles and antiparticles that constantly pop in and out of existence in empty space, following Heisenberg's uncertainty principle. According to Einstein's theory of relativity, this vacuum energy should have a gravitational effect, meaning it contributes to the cosmological constant. This, in turn, is believed to be one of the main reasons the universe's expansion is speeding up. However, there's a massive problem. When physicists use quantum field theory to predict how much vacuum energy should exist, they come up with a number that is vastly larger than what is actually observed. This enormous gap between theory and reality remains one of the biggest unsolved problems in modern physics. Regardless of what dark energy truly is, for it to drive the accelerated expansion of the universe, it must have an extremely strong negative pressure. In general relativity, pressure acts similarly to mass when it comes to its gravitational effects. Both pressure and mass are part of something called the stress-energy tensor, which determines how matter and energy influence gravity. In the case of dark energy, this negative pressure works against gravity, causing space to expand at an increasing rate. If the universe were shrinking instead, this same pressure would slow down its contraction. This phenomenon is sometimes called gravitational repulsion because it seems to push everything apart, counteracting the usual pull of gravity. When we break down the universe into its main components, we find that everything we know falls into three broad categories: matter, radiation, and dark energy. Matter includes everything that has mass, from stars and planets to tiny dust particles. As the universe expands, the energy density of matter decreases in proportion to the cube of the expansion factor. Imagine you have a box filled with particles. If the box doubles in size, the energy of the particles inside doesn't just get cut in half, it decreases by a factor of 8 because the volume increases in 3 dimensions. Radiation, which includes light and heat, behaves a little differently. As space expands, the energy of radiation decreases even faster than that of matter. This is because, in addition to spreading out over a larger volume, the waves of light and radiation get stretched. This stretching effect, called redshift, makes the radiation lose energy more quickly than matter does. Dark energy, on the other hand, does something completely different. Unlike matter and radiation, its energy density doesn't decrease as the universe expands. Instead, it stays the same, no matter how large the universe gets. In other words, while matter gets diluted as space grows, dark energy remains constant, filling the void evenly and continuously driving the universe's acceleration. Scientists have gathered several lines of evidence that support the existence of dark energy, even though it hasn't been directly detected. Distance and redshift measurements. By studying how the light from distant objects has been stretched over time, scientists have discovered that the universe has expanded more rapidly in recent history than it did in the past. This suggests that something, likely dark energy, is causing this accelerated expansion. The need for extra energy. The universe appears to be flat in shape, meaning it doesn't curve inward or outward. In order for the universe to be flat, there must be a specific amount of total energy present. Since visible matter and dark matter don't provide enough energy to meet this requirement, scientists believe dark energy must be making up the difference. Patterns in cosmic structures. When astronomers study the large-scale arrangement of galaxies and cosmic structures, they find patterns that suggest dark energy is at work. The way galaxies are distributed throughout space provides additional clues about the expansion of the universe and the mysterious force driving it. In the year 1998, a group of astronomers known as the High Z Supernova Search Team made a shocking discovery while studying a special type of exploding star called Type Ia supernovae. They expected to find that the universe's expansion was slowing down due to gravity, but instead, they found the opposite. The universe was actually expanding faster and faster. Just 1 year later, in 1999, another team of researchers, the Supernova Cosmology Project, reached the same surprising conclusion. Their groundbreaking work reshaped our understanding of the cosmos and earned them the prestigious Nobel Prize in Physics in the year 2011. Since then, many other scientific observations have reinforced this discovery. Studies of the cosmic microwave background, faint radiation left over from the Big Bang, have provided strong evidence. Additionally, astronomers have examined how light bends around massive objects in space, a phenomenon called gravitational lensing, and have analyzed the large-scale structure of the universe. All these findings support the idea that a mysterious force called dark energy is driving the universe's accelerating expansion. Some skeptics argue that the strongest proof comes only from measuring redshift, the way light stretches as objects move away, and the distances of supernovae. However, other evidence, such as patterns in the cosmic microwave background, also suggests that the universe is expanding faster than it would without dark energy. Supernovae are incredibly useful for studying the universe because they act like natural measuring tools, often referred to as standard candles. Scientists know exactly how bright these explosions should be, which allows them to determine how far away they are. By comparing the distance of a supernova with how much its light has been stretched, its redshift, astronomers can accurately track how fast the universe is expanding. Type Ia supernovae are particularly valuable because they always explode with the same brightness, making them among the most reliable cosmic markers. Recent measurements indicate that dark energy makes up around 71% of the universe, while the remaining 29% consists of dark matter and ordinary matter. The leading theory that explains how galaxies, stars, and other cosmic structures form suggests that matter only accounts for about 30% of the universe's total critical density, the amount needed for the universe to be geometrically flat. More proof of dark energy came in the year 2011 from the Wigglesy Galaxy Survey, which studied over 200,000 galaxies. Researchers used an innovative technique to measure distances to galaxies located as far as 2,000 million parsecs away. Their results further confirmed that the universe has been expanding at an increasing rate, providing even stronger support for the idea of cosmic acceleration. For the universe to be as flat as it appears, there must be some additional form of energy filling the cosmos. All the observable matter, both regular and dark, accounts for only about 30% of what is needed. The remaining 70% is believed to be dark energy. Data from the Wilkinson Microwave Anisotropy Probe, a spacecraft that mapped the early universe, estimated that dark energy makes up about 73% of the universe. More recent findings from the Planck satellite refined this estimate, suggesting that dark energy constitutes approximately 68%, while dark matter makes up about 27%, and regular matter accounts for just under 5%. Dark energy also helps explain strange patterns in the cosmic microwave background. When light particles, known as photons, travel through regions of intense gravity, such as galaxy clusters or vast empty spaces, they lose or gain energy. This effect creates temperature variations in the background radiation and is known as the integrated Sachs-Wolf effect. It is considered another major clue pointing to the presence of dark energy. Scientists have also started using a new method to study dark energy by measuring the Hubble constant, which describes how the universe's expansion rate changes over time. They focus on galaxies that have evolved in a predictable way, treating them as cosmic clocks. By analyzing their ages and redshifts, researchers can estimate the universe's expansion at different points in its history. Despite all this evidence, dark energy remains one of the greatest unsolved mysteries in physics. Scientists agree that it plays a crucial role in driving the universe's accelerating expansion, but they still do not fully understand what it is or how it works. To find answers, researchers are exploring multiple possibilities. Some are revisiting Einstein's theory of gravity to see if modifications are needed. Others are trying to uncover the exact properties of dark energy, while some are even considering alternative explanations based on unexpected cosmic observations. One of the simplest ideas about dark energy is that it is a fundamental feature of space itself. According to this view, even completely empty space contains a form of energy, often called vacuum energy. This concept is known as the cosmological constant and is represented by the Greek letter lambda. It serves as the foundation of the lambda CDM model, which is currently the most widely accepted explanation of the universe's structure. Since Einstein's famous equation shows that energy and mass are connected, this vacuum energy should have a gravitational effect, influencing how the universe expands. However, there is a huge problem with this idea. The calculations from quantum physics suggest that the amount of vacuum energy should be incredibly large, about 120 orders of magnitude higher than what is observed. If that were true, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. Yet, we exist in a universe where structures have formed and evolved over billions of years. Something must be balancing out most of this energy, but not completely cancelling it. Scientists do not yet know why this happens, making dark energy one of the biggest puzzles in modern physics. While many assume that dark energy is a constant, unchanging force, some physicists believe it could be something far more dynamic, an evolving energy field that changes over time. This idea is known as quintessence. Unlike the cosmological constant, which remains the same everywhere, quintessence behaves like an energy field spread across the universe, influencing its expansion in different ways at different times. It is thought to be extremely light, so that, unlike normal matter, it does not clump together to form stars and galaxies. Some versions of this theory suggest that the universe's expansion is happening slightly slower than what the standard model predicts. However, there is still no solid proof to confirm or disprove this idea. One of the biggest unanswered questions about dark energy is why it became dominant at this particular moment in cosmic history. If it had taken over too soon, the universe's rapid expansion could have prevented galaxies from forming, and life as we know it might never have existed. Some scientists think this is just a coincidence, while others believe it supports a controversial idea called the anthropic principle, the notion that the universe must be the way it is because we are here to observe it. Interestingly, some quintessence models include a built-in mechanism, known as a tracker, that naturally explains why dark energy became influential at this specific time. According to these models, dark energy's behavior is linked to the density of radiation in the early universe, which could explain its delayed but powerful emergence. Some extreme versions of quintessence predict even stranger scenarios. One of these is phantom energy, a type of dark energy that becomes stronger over time instead of staying the same. If this idea is correct, the universe wouldn't just keep expanding, it would eventually be torn apart in a terrifying event called the Big Rip. In this doomsday scenario, the force of expansion would grow so strong that it would first tear apart galaxies, then stars, then planets, and finally even atoms themselves, reducing everything to nothingness. Another version of quintessence, known as K-essence, suggests that dark energy could be made of unusual energy forms that behave in ways never seen before. Some variations of K-essence even propose the existence of negative kinetic energy, which could have bizarre and unpredictable effects on the evolution of the universe. In recent years, astronomers have discovered inconsistencies in the measurements of the universe's expansion rate. This disagreement, known as the Hubble tension, suggests that the standard model of cosmology might be missing something important. Some researchers believe that only specific types of quintessence models with additional interactions can explain this discrepancy. Even though dark energy remains one of the biggest mysteries in modern physics, it is deeply connected to Albert Einstein's theory of general relativity. Some scientists argue that if general relativity were modified in certain ways, we might not need dark energy at all to explain the universe's accelerating expansion. Several alternative theories have been proposed, but so far, none have been fully proven. In fact, a key discovery, the detection of gravitational waves from the event known as GW 170817, has already ruled out many of these modified gravity theories. According to astrophysicist Ethan Siegel, while alternative ideas about dark energy often make headlines, most experts in the field still believe that dark energy is real. Competing theories simply do not match observational data as accurately as the current model. Scientists estimate that the universe's expansion started accelerating around 5 billion years ago. Before that, gravity, mainly from dark matter and normal matter, was slowing everything down. But as the universe grew larger, dark matter spread out and became less influential, while dark energy remained nearly unchanged. Eventually, dark energy took over, causing the expansion to speed up. For every time the universe doubles in size, the amount of dark matter in a given space is cut in half, but dark energy stays nearly the same. What happens next depends on the nature of dark energy. If it remains constant, like the cosmological constant suggests, the universe will keep expanding forever. Distant galaxies will move away from us faster and faster, eventually reaching speeds greater than light itself. This does not break any laws of physics because space itself is stretching rather than the galaxies moving through space. Right now, scientists estimate that the cosmological event horizon, the distance beyond which we can never receive signals or light, is about 16 billion light-years away. If something happens within that range, its light may still reach us in the distant future. But anything happening beyond that distance will be lost to us forever. As galaxies approach this horizon, the light they emit will be stretched into longer and longer wavelengths, eventually becoming invisible. To an observer in the far future, those galaxies will appear to fade away until only our own local group of galaxies remains in an otherwise empty universe. While the idea of an endlessly expanding, dark, and empty universe is unsettling, some alternative theories predict more dramatic endings. If dark energy keeps growing stronger, the Big Rip could become reality, shredding everything in existence. But there are also theories suggesting that dark energy might change over time, possibly reversing its effects. In that case, the universe could stop expanding and begin collapsing in a big crunch, eventually shrinking back into a single point, possibly leading to another Big Bang and the birth of a new universe. Another possibility is that dark energy follows cycles, causing the universe to expand and contract in an endless loop of Big Bangs and big crunches. The anthropic principle is a concept in cosmology that suggests the universe must have the necessary conditions for life, because, if it didn't, no one would be here to observe it. In other words, the universe appears to be fine-tuned for life simply because only a universe capable of supporting life would allow conscious beings to exist and ask questions about it. Supporters of the anthropic principle argue that this idea helps explain why the universe has a certain age and specific physical constants that make life possible. If these numbers were different, even slightly, intelligent life might never have emerged. For example, if the universe were much younger, there wouldn't have been enough time for stars to create the heavier elements needed for planets and living beings. If it were much older, most stars would have burned out, and planetary systems like ours might not exist. Scientists have long wondered why the fundamental physical constants, the unchanging numbers that govern physics, have the precise values they do. The anthropic principle suggests that they had to be this way because only a universe with these conditions could support life. It's not that the universe was designed specifically for life, but rather that life could only appear in a universe with the right conditions. There are multiple ways to interpret the anthropic principle. Some scholars, like philosopher Nick Bostrom, have counted around 30 different versions of it. However, they generally fall into two main categories. The weak anthropic principle. This simply states that we observe a universe suited for life because life only emerges in such a universe. The strong anthropic principle. This suggests that the universe must, in some way, be structured to produce life. The principle itself arose from observations that the universe's laws and constants seem perfectly suited for life as we know it. It's an argument based on hindsight. If the universe couldn't support life, we wouldn't be here to discuss it. Some critics argue that calling it the anthropic principle is misleading. The term comes from the Greek word anthropos, meaning human, but the principle doesn't suggest that the universe is designed specifically for human life. Instead, it applies to any form of life, not just humans or carbon-based creatures. It would work just as well for alien life forms, stars, or even galaxies. The anthropic principle has sparked debates, mainly because different versions of it have been used to argue different things. Some critics feel that the principle discourages deeper scientific investigation. For example, the weak anthropic principle is sometimes criticized for being unscientific because it can't be tested or proven false. On the other hand, stronger versions make bold claims that remain controversial because they depend on evidence that is difficult to verify. In 1961, physicist Robert Dicke pointed out that the universe must have a specific age suitable for life. If it were 1/10 of its current age, elements like carbon wouldn't have had time to form, and planets like Earth wouldn't exist. If the universe were 10 times older, most stars would have died, leaving behind mostly white dwarfs and dim red stars, making it unlikely for planetary systems to survive. Dicke also suggested that the universe's matter density must be close to a critical density, just enough to prevent it from collapsing in a big crunch, but not too much to stop it from expanding. More recent studies suggest that normal matter makes up around 30% of this critical density, while the rest is likely due to dark energy. In the late 20th century, physicist Steven Weinberg offered an anthropic explanation for the mysterious cosmological constant, a number that determines how fast the universe expands. The predicted value of this constant from particle physics is vastly different from the one we actually observe, by a factor of 120 orders of magnitude. This has been called the worst prediction in physics. However, Weinberg noted that if the cosmological constant were just a bit larger, the universe would have expanded too fast, preventing the formation of stars and planets, and thus life. Some scientists argue that the physical constants governing the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, appear to be precisely balanced to allow life to exist. If, for example, the strong nuclear force were increased by just 50%, it would drastically alter the formation of elements in stars, preventing the creation of hydrogen, the key ingredient for water and life as we know it. Similarly, small changes in the other forces would have dramatic effects on the universe's age, structure, and ability to support life. The term anthropic principle was first used by Brandon Carter, a theoretical physicist, at a 1973 conference honoring the 500th birthday of Copernicus. Carter introduced the concept as a counterargument to the Copernican principle, which states that humans do not occupy a special or central place in the universe. Carter suggested that, while humans may not be the center of the universe, the conditions we observe must still be somewhat privileged because they allow for intelligent life to exist. At the time, the steady-state theory, which claimed that the universe looks the same in all directions and has always existed, was still popular. But this theory was overturned in 1965 with the discovery of the cosmic microwave background radiation, clear evidence that the universe has changed over time, likely starting with the Big Bang. In the year 1973, physicist Brandon Carter introduced two different ideas under what he called the anthropic principle. The first, which he called the weak anthropic principle, suggested that humans only exist in specific locations in space and time because those places happen to be suitable for life. The second, more controversial idea, the strong anthropic principle, went even further. It proposed that the fundamental constants of physics, the very numbers that govern the universe, might be set in a way that allows life to exist. At first glance, the weak version makes sense. After all, humans could have evolved in any number of places and times as long as conditions were right. But when applying the strong version, things get tricky. There is only one known universe with a fixed set of physical laws, so why do those laws allow life at all? Carter suggested two possible answers. First, humans can make educated guesses about the physical constants of the universe based on the fact that they exist within it. But if that doesn't seem like a complete answer, there's a second possibility. Maybe there isn't just one universe. Maybe there are many, possibly an infinite number, each with its own set of physical laws. This idea, now called the multiverse theory, though Carter originally called it the world ensemble, would mean that our universe is just one among countless others, and we happen to live in one that allows life to exist. This concept is bold, even radical, but it provides a potential answer to a deep mystery. Why do the laws of physics seem so perfectly tuned to allow life? If there are countless universes, most of them would be unsuitable for life, but a few would be just right. Naturally, humans would only exist in one of the just right universes, so we shouldn't be surprised to find ourselves in one. Since Carter's paper, the anthropic principle has taken on many different meanings. A major turning point came in the year 1986, when scientists John D. Barrow and Frank Tipler redefined the weak and strong anthropic principles in ways that differed from Carter's original ideas, leading to confusion in the scientific community. However, Carter was far from the first person to consider these ideas. As early as the year 1904, evolutionary biologist Alfred Russel Wallace suggested that the universe might need to be as vast and complex as it is in order to create a world that could support human life. Then, in the year 1957, physicist Robert Dicke pointed out that the age of the universe isn't random. Biological factors determine why we exist at this particular moment in cosmic history. He also noted that if the fundamental constants of physics were slightly different, humans would never have existed to ask these questions in the first place. Even before these scientists, Austrian physicist Ludwig Boltzmann had explored similar ideas in the late 19th century. Boltzmann was puzzled by why the universe seemed to have such low entropy, a measure of disorder, when thermodynamic principles suggested it should be far more chaotic. He proposed that random fluctuations could create temporary pockets of low entropy, tiny, isolated regions where order briefly emerges from chaos. He argued that humans happen to exist in one of these rare, orderly regions, simply because it's the only kind of place where intelligent life could arise. Carter's version of the anthropic principle has generated a lot of debate, partly because it relies on a simple but easily misunderstood idea. The universe seems fine-tuned for life, so maybe it actually is. Scientists such as Stephen Hawking and Michael Collins describe this as the possibility that there isn't just one universe, but an infinite collection of universes, each with different initial conditions. If this idea is true, then the reason our universe appears so finely tuned is simply that we wouldn't be here to notice it otherwise. Most universes wouldn't support life, but in an infinite multiverse, at least a few would, ours included. Though philosophers have pondered similar ideas for centuries, by the early 1970s, the only scientific theory that allowed for multiple universes was the many-worlds interpretation of quantum mechanics. This theory suggests that every quantum event creates branching timelines, but it doesn't allow for variations in fundamental physical constants. Since then, however, new theories have emerged. In the 1980s, the combination of inflation theory and symmetry breaking in the early universe provided a mechanism for how physical constants could vary across different regions of space. By the early 21st century, string theory introduced an even more dramatic possibility. What if every fundamental constant, including the number of spatial dimensions, could vary across an unimaginably vast landscape of possible universes? This idea stands in contrast to the traditional goal of physicists, finding a single, all-encompassing theory of everything with no free parameters. Albert Einstein once asked whether God had any choice in setting the laws of physics. In other words, was the universe designed to be exactly the way it is, or could it have been different? In the year 2002, some physicists working on string theory believed they were close to eliminating the need for the anthropic principle. But by the next year, scientist Leonard Susskind argued that the opposite might be true, that the complexity of the landscape of possible universes actually made the anthropic principle seem more credible than ever. The anthropic principle also plays a role in debates about intelligent design. Supporters of intelligent design often point to the fine-tuning of the universe as evidence of a creator. Critics, however, argue that fine-tuning might not be as remarkable as it seems. Some believe that the universe isn't actually as finely tuned as claimed, while others suggest that even if it is, this doesn't necessarily prove the existence of an intelligent designer. Some even argue that the anthropic principle itself weakens the case for intelligent design because it provides an alternative explanation for why the universe supports life. Brandon Carter's weak anthropic principle isn't something that can be tested through observation. It's more of a guiding principle for scientists. On the other hand, the strong anthropic principle suggests that the universe is somehow required to support life. Testing this idea would require finding evidence of life in other universes. But since most definitions of universe imply that we can't observe others, this creates a major problem. The theory might be impossible to prove or disprove. Philosopher John Leslie once made a series of predictions based on the strong anthropic principle, suggesting that the laws of physics will turn out to be determined by chance rather than by strict necessity. Theories proposing multiple universes will continue to gain scientific support. More evidence for fine-tuning in the universe will keep accumulating. No forms of life based on non-carbon chemistry will ever be discovered. Mathematical studies of galaxy formation will confirm that the expansion rate of the universe is crucial for shaping its structure. Some scientists, like Craig Hogan, argue that it would be extremely strange if all fundamental constants were rigidly fixed, since that would leave no room for an explanation of fine-tuning. If that were the case, humans might be forced to accept the idea that the universe simply had to be this way in order to support life, whether we like it or not. The famous astronomer Fred Hoyle might have used a special way of thinking, known as anthropic reasoning, to make an astonishing prediction about the stars. He noticed that life on Earth depends on a chemical element called carbon, specifically a type known as carbon-12. Since carbon is so important for life, he reasoned that there must be an unknown process inside stars that makes it easier for carbon-12 to form. He focused on a particular reaction in stars called the triple alpha process, which creates carbon from smaller helium atoms. Based on this idea, Hoyle predicted that there must be a hidden energy level, or resonance, in carbon-12 that makes this process work efficiently. He even calculated that this energy level should be about 7,600,000 electron volts. Soon after, a research team led by Willie Fowler discovered that this energy level really existed, and their measurements closely matched Hoyle's prediction. However, in the year 2010, a historian of science named Helga Krag argued that Hoyle had not actually used anthropic reasoning when he made his prediction in the year 1953. Krag pointed out that anthropic reasoning, the idea that the universe appears fine-tuned for life, did not become widely discussed until the year 1980. He claimed that Hoyle and other scientists only made the connection between carbon and life after the resonance had already been discovered. Krag referred to this idea as an anthropic myth. Another fascinating debate in cosmology involves the theory of cosmic inflation, which explains how the universe expanded extremely rapidly in its earliest moments. A physicist named Don Page criticized this idea by pointing out a major problem. For time to flow in one direction, from past to future, the universe must have started with an incredibly low level of disorder or entropy. But this starting condition seems extremely unlikely, making the entire inflationary theory questionable. However, physicist Paul Davies disagreed. He argued that an inflationary version of the anthropic principle solves this problem. Davies accepted that the early universe had to be extremely orderly, essentially a tiny, well-organized patch of space that then expanded into the universe we see today. He believed that this actually strengthened the inflationary theory, since it removed the need for extra assumptions about how the universe began, assumptions that other Big Bang theories still require. Another major idea in modern physics comes from string theory, which suggests that instead of just one universe, there may be an enormous number of possible universes. These different universes, known as vacua, or backgrounds, form what scientists call the multiverse, or the string landscape. Physicist Leonard Susskind argued that if there are countless universes, then anthropic reasoning makes sense, because we only exist in a universe that has the right conditions for life. If other universes do not support life, we simply never notice them. Renowned physicist Steven Weinberg saw the anthropic principle as an important shift in scientific thinking. He believed that cosmologists who do not believe in a divine creator could use the principle to explain why the fundamental constants of nature seem perfectly suited for life. He called it a turning point in modern science because it could explain the precise values of these constants without needing to assume that a higher power carefully fine-tuned them. However, not everyone agreed. Scientists like David Gross, Lubos Mottl, Peter Voigt, and Lee Smolin argued that this way of thinking does not actually predict anything useful. Meanwhile, researchers such as Max Tegmark, Mario Livio, and Martin Rees pointed out that many widely accepted scientific theories cannot be fully tested yet, but they are still considered valid. Between the years 2000 and 2002, a scientist named Jürgen Schmidhuber highlighted another perspective. He referred to Ray Solomonoff's theory of universal inductive inference, which provides a logical way to evaluate scientific theories based on limited observations. Schmidhuber argued that this method already gives scientists the best possible way to judge which theories are most reliable, even if they cannot test everything directly. Two researchers, Jiwei Wang and Samuel L. Braunstein, explored the idea that life's existence in the universe depends on certain fundamental physical constants. Their findings suggested that if scientists do not fully understand these constants, they might mistakenly think that the universe was deliberately designed for life. This challenges the idea that our universe is uniquely special, because if different constants could also allow life in other universes, then ours may not be as rare as it seems.